Imagine waking up to a critical production outage where your machine learning model suddenly begins making erratic predictions, despite not a single line of feature logic or model architecture changing. When you inspect the deployment, the git commit hash is identical and the incoming data payload is intact, but the operating system's dynamic loader loaded a mismatched C library during an automated server restart. This hidden fragility is why machine learning engineering starts long before writing code. It begins at the memory and environment boundary. A machine learning project is rarely just Python code. It is a complex tapestry of interpreted high-level logic, compiled C and C++ extensions, optimized Fortran math routines, and hardware-accelerated CUDA libraries. When these underlying components conflict, your code fails in subtle, frustrating, and seemingly unpredictable ways. Understanding how environment isolation works at a low level is not merely an administrative chore. It is the foundational engineering skill that guarantees your machine learning workflows are deterministic, scalable, and reproducible across different machines and deployment targets. To understand environment isolation, we must first look at how the Python interpreter discovers and loads modules. When you execute a Python process, the interpreter initializes a search path known as system path. This path is an ordered list of directory locations where Python looks whenever you issue an import statement. At the top of this list is the directory containing the running script itself, followed by standard library locations, and finally a specialized directory known as site packages. In an unisolated global environment, every package you install via a package manager is dumped into this single shared site packages directory. If Project A requires version 1.0 of a numerical library and Project B requires version 2.0 of the exact same library, a global setup forces you into an impossible choice. Installing one version silently overwrites the other, breaking project dependencies and introducing severe runtime instability. A virtual environment solves this fundamental collision by isolating the Python executable and its site packages directory. Spatializing this structure, imagine a virtual environment as an isolated directory tree on your file system. At the root of this tree is a binaries folder containing a standalone Python interpreter executable, or a symbolic link pointing back to a specific base Python installation. Alongside this binary sits an isolated site packages directory, completely divorced from the global system installation. When you activate a virtual environment, your shell modifies its environment variables, specifically prepend-ing the virtual environment's binary directory to the system path environment variable. Setting virtual environment binary directories at the head of the system path environment variable ensures that whenever subprocesses execute system commands, execution resolves to localized binaries rather than system-wide utilities. Consequently, when you type Python or call package tools in your terminal, the operating system intercepts the command and routes execution to the localized interpreter inside your environment folder. In enterprise deployment pipelines, auditing environment variables during initialization prevents host platform pollution, guaranteeing deterministic binary execution across heterogeneous cloud clusters. Inside this localized process, Python dynamically updates its system path variable so that all import lookups are directed exclusively to the environment's isolated site packages directory. If a package is not installed within this specific directory tree, the interpreter cannot import it, even if that package exists globally on your machine. This guarantees strict boundary isolation. Furthermore, when the interpreter initializes, it parses a configuration file located at the environment root named pyvenv, CFG. This configuration file stores critical metadata, including the home path of the underlying base Python installation, the exact Python version, and flags indicating whether global site packages should be visible or hidden. By toggling these internal flags, the virtual environment enforces complete independence from system-level Python packages. Virtual environment path resolution relies on sys.prefix and sys.base_prefix interpreter attributes. When Python runs inside an isolated virtual environment, sys.prefix points to the virtual environment's root directory, while sys.base_prefix points to the underlying base Python installation directory. If code inspects these attributes, it can programmatically verify whether execution is bound to an isolated environment or a global base installation. Machine learning environments require an even deeper layer of isolation than standard web applications because machine learning packages depend heavily on native C, C++, and Fortran shared dynamic libraries. Libraries like NumPy and SciPy do not perform matrix multiplication using pure Python loops. They delegate heavy computations to low-level compiled libraries such as OpenBLAS, Intel MKL, or Apple Accelerate. Standard Python virtual environments created through native tools isolate Python files and compiled C extensions, but they rely on your host operating system's package manager to provide underlying C libraries and hardware drivers. This is where binary environment managers like Conda, Mamba, and Pishi diverge fundamentally from native virtual environments. A Conda environment does not merely manage Python packages. It acts as a cross-platform binary package manager. When you install a library within a Conda environment, the package solver retrieves precompiled binary packages that bundle not only the Python binding files, but also the exact shared object or dynamic link library files required at the system level. Spatializing a Conda environment, visualize a self-contained operating system root inside a single directory. It contains its own lib directory for shared C libraries, its own include directory for C header files, and its own bin directory for executable tools like compilers or CUDA runtimes. Because Conda isolates system-level C dynamic libraries within the environment folder, two different Conda environments on the same machine can run entirely different versions of low-level C libraries without interfering with each other or touching system root directories. Additionally, Conda package recipes defined via meta.yaml specify exact build requirements, run requirements, and host requirements. Host requirements declare C libraries required at compilation time, while run requirements specify shared objects needed when executing binaries in production. Dynamic shared object isolation on Unix systems requires careful manipulation of ELF binary headers. To understand what an ELF binary header is, imagine it as a built-in digital passport at the front of a Linux executable file. This header contains essential metadata telling the operating system's dynamic loader exactly which external dynamic libraries the binary needs and where to find them in memory. When a C extension is compiled, the linker can embed an repath or runpath attribute directly into the shared object header. Repath specifies an absolute or relative directory search path that the dynamic linker checks before evaluating system library directories. By embedding relative runpath entries pointing to the environment's lib directory, binary package managers ensure that C extensions resolve shared objects locally within the environment tree, bypassing global system C libraries completely and preventing system-level library mismatch crashes. Dynamic loading of shared C libraries via types.cdll or CFFI interfaces allows Python applications to bind to low-level compiled C functions at runtime. When loading a shared object, the dynamic loader inspects ELF binary symbol tables, resolving function pointer addresses in memory. On Windows systems, the dynamic link library loader evaluates DLL search orders, checking the directory containing the running executable, current working directories, system directories, and path environment variables. Dependency resolution mechanics further illustrate the complexity of environment management. Traditional package tools utilize SAT solver algorithms or PubGrub resolution engines to inspect dependency metadata trees across candidate packages. To explain SAT solvers and PubGrub in simple terms, they are mathematical constraint-solving engines that solve the puzzle of finding compatible package versions across dozens of interconnected, dependent libraries. When resolving a complex machine learning dependency graph containing dozens of interconnected libraries, the solver evaluates version compatibility constraints. If package A requires package C version less than 2, while package B requires package C version greater than 2.5, a dependency conflict occurs. Modern Rust-based package tools like UV execute dependency resolution using high-speed SAT solvers. Parsing will metadata in parallel to resolve dependency graphs up to 100 times faster than legacy installers, while producing deterministic lock files. Modern Rust-based installers execute parallel HTTP range requests against PyPI index servers. Caching will metadata locally in binary key value stores. This metadata caching eliminates network latency during subsequent environment builds, allowing continuous integration pipelines to recreate environments in milliseconds. Package index security and hash checking modes protect deployment pipelines from tampered packages. When hash checking mode is enabled in package managers, the installer refuses to install any wheel or source distribution unless its cryptographic SHA-256 hash matches the hash recorded in the lock file. This security boundary prevents man-in-the-middle attacks and repository tampering, ensuring that production servers execute identical binary code. Package lock file validation routines inspect transitive dependency trees to detect version drift before deployment execution begins. Enforcing strict lock file synchronization guarantees bit-for-bit software environment parity across local development workstations, staging environments, and production cloud infrastructure nodes. Furthermore, system path evaluation order follows strict array priority. Local directory paths take precedence over site packages, requiring clean path isolation to prevent local script names from shadowing standard library modules. Subshell environment variable inheritance governs process isolation when launching subprocesses from Python scripts. When a Python script spawns a child process using subprocess execution libraries, the child process inherits a copy of the parent process's environment variables. Modifying environment variables within a subshell alters variable state for child processes, but leaves parent shell variables unmutated. Will packaging specifications define how precompiled C extensions are distributed across operating systems? A wheel artifact is a specialized zip archive containing compiled binary shared objects, Python module files, and metadata descriptors. Will file names include explicit application binary interface, or ABI tags? To put ABI tags in simple terms, an ABI tag is a compatibility signature that guarantees a compiled C extension matches the exact C compiler standards, CPU architecture, and Python version of your host system, preventing binary mismatch crashes. For example, a wheel tagged for many Linux 2014 guarantees that its embedded C shared objects were compiled against a standardized, backward-compatible GNU C library version, ensuring the binary executes reliably across diverse Linux distributions without requiring local C compiler compilation. System customization hooks add another dimension to initialization mechanics. When Python starts, it checks for initialization scripts named sitecustomize.py and usercustomize.py inside site packages. These customization scripts allow platform administrators to inject global configuration settings, register custom import hooks, or configure telemetry before user code executes. Multi-stage Docker builds enforce clear environment isolation between compile-time toolchains and runtime execution. During the initial build stage, heavy compilation tools like GCC, CMake, and CUDA headers compile custom C extensions into wheels. The final production image copies only the precompiled binary artifacts into a minimal runtime base image, shedding compiler bloat and shrinking container image size from several gigabytes down to a few hundred megabytes while hardening the security boundary. Furthermore, binary wheel validation tools like Audit Wheel perform ELF dynamic library inspection on compiled Linux wheels. When a C extension links against shared libraries on a build machine, Audit Wheel analyzes repath headers and shared object symbol references. It copy embeds external dynamic libraries directly into the wheel archive and updates internal runpath headers to relative origin paths, converting non-standard wheels into self-contained many Linux wheels that execute reliably across diverse Linux server distributions. Operating system dynamic linkage auditing involves inspecting shared object symbol tables using tools like LDD and readelf on Linux platforms, verifying that precompiled dynamic libraries resolve symbols from environment lib folders rather than system root directories. When working within interactive development interfaces like Jupyter Notebooks and VS Code, an additional layer of architectural abstraction comes into play: the kernel architecture. A common misconception among emerging engineers is that opening a Jupyter Notebook inside a specific folder automatically ties code execution to the virtual environment of that folder. In reality, Jupyter decouples the user interface from code execution using a client-server paradigm connected via 0MQ messaging sockets. The browser or editor displays the notebook frontend, while a background process called a kernel executes the Python code. This kernel is launched as a distinct operating system process. When a notebook cell runs, the frontend serializes the code string into a JSON payload and transmits it over a 0MQ socket to the kernel process. To bind a notebook to an isolated environment, an explicit kernel specification file must be registered, pointing the execution path directly to the virtual environment's Python executable. Moving from internal mechanics to engineering design decisions, architects must carefully evaluate the trade-offs between different environment management strategies. The primary trade-off exists between native lightweight virtual environments combined with fast package installers versus full binary environment managers like Conda, Mamba, or containerization platforms like Docker. Native virtual environments combined with modern Rust-based package tools like UV offer astonishing speed and minimal storage overhead. Package resolution and installation occur in a fraction of a second, relying on pre-built WIL files stored in central repositories. For projects that only require standard Python libraries with standard precompiled wheels, native virtual environments are extremely efficient, easy to automate in continuous integration pipelines, and lightweight to audit. However, native Python package tools encounter severe limitations when dealing with complex non-Python binary dependencies, specific CUDA library bindings, or legacy C++ packages that do not provide platform-specific WIL distributions. In these scenarios, Attempting to install packages via source wheels often triggers a fallback to source compilation. If the developer's machine lacks the exact C compiler version, CMake tools, or header files expected by the package, installation fails with cryptic compilation tracebacks. Conda and Pishi mitigate this pain point by distributing precompiled binary packages across multiple platforms. The engineering trade-off for this convenience is larger disk usage, slower dependency resolution times when using legacy solvers, and potential channel conflicts if packages are mixed indiscriminately between default channels and community-maintained channels like CondaForge. Another critical architectural decision revolves around lock file management and deterministic reproducibility. In professional software development, declaring abstract high-level dependencies in a configuration file is insufficient for production systems. For instance, listing a numerical processing library without specifying an exact version constraint allows package installers to pull whatever latest minor or patch version exists at the moment of installation. If an upstream dependency introduces a subtle breaking change or alters a numerical precision default, your data preprocessing pipeline can produce different results on a production server than it did on a local developer workstation. Dynamic versioning in modern Python package builds relies on tools like subtuples_scm, which extract version metadata dynamically from Git tags during will compilation, eliminating hard-coded version strings in source files. To prevent this drift, modern machine learning workflows enforce strict lock file mechanisms. A high-level manifest specifies direct dependencies and version bounds, while a generated lock file records the exact transitively resolved dependency tree, including precise version numbers, source hashes, and platform markers for every single package and subdependency. When a team member or continuous integration worker synchronizes their environment against a lock file, the package manager bypasses dynamic dependency solving altogether. It installs the exact binary hashes specified in the lock file, ensuring bit-for-bit environment parity across all development and production environments. In a production case study, consider a financial services enterprise building an automated credit risk scoring pipeline. The data engineering team ingests millions of streaming transactional records per minute, passing raw data through a feature transformation pipeline written in Python. This pipeline relies on high-speed C extensions for real-time feature normalization, requiring exact CUDA dynamic library linkages for GPU acceleration. During initial deployment, the engineering team relied on unconstrained environment setup scripts that ran dynamic package installations upon container startup. This design flaw led to a major production outage. An upstream package repository published a minor patch update to a core numerical dependency overnight. When auto-scaling policies triggered the spin-up of new worker nodes, the newly provisioned instances fetched the updated patch version, while existing worker nodes continued running the older version. The minor patch subtly altered how floating point rounding was handled in a sparse matrix normalization routine. As a result, worker nodes running on identical hardware produced slightly divergent feature values for the same incoming transactions, triggering downstream classification inconsistencies and causing systemic transaction scoring failures. The engineering team resolved this vulnerability by re-architecting their environment delivery strategy into a multi-stage production pipeline. First, they migrated to an isolated binary package specification managed by strict lock files. They defined the base environment including specific CUDA runtimes, C++ compiler libraries, and Python binaries within a reproducible manifest. In their automated build pipeline, a dedicated staging process resolves dependencies once, generates a cryptographic lock file, and builds a fully compiled, self-contained container image where the environment site packages and shared C binaries are pre-installed and frozen. Production deployment scripts no longer execute package installations at runtime. Instead, worker instances pull the pre-validated immutable image. By decoupling environment resolution from runtime execution and enforcing lock file immutability, the enterprise eliminated non-deterministic pipeline behavior and guaranteed absolute cross-node consistency. Troubleshooting and debugging environment failures requires a systematic understanding of environment variables, binary resolution order, and dependency isolation patterns. One of the most prevalent failure modes in data science workstations occurs when multiple package managers or channels compete for control of the same environment. For example, installing a package via Conda and subsequently installing another package or an update into the same environment via pip can corrupt binary links. Conda tracks installed files through explicit metadata manifests inside the environment directory. When pip installs or updates a package, it operates independently of Conda's internal tracking database, potentially overwriting C dynamic libraries or Python modules without updating Conda's registry. This leads to binary mismatch errors, such as symbol lookup errors or segmentation faults, when C extensions attempt to invoke functions in mismatched shared libraries. To diagnose and resolve binary link corruption, developers must audit their execution context by inspecting the active Python interpreter path and the loaded module paths directly. Running an inline check on the executable path verifies whether the operating system invoked the intended virtual environment interpreter or fell back to a system-level binary. Furthermore, inspecting system path reveals the exact directory evaluation hierarchy. If a user site packages directory appears early in the system path hierarchy, packages installed in the user's home directory will take precedence over packages inside the active virtual environment, creating phantom import behaviors where updating a package in the virtual environment seems to have no effect on code execution. Another frequent failure mode involves Jupyter kernel mismatch, where code executed inside a notebook interface uses a different Python environment than the terminal command line where packages were installed. This issue manifests as a module not found error inside a notebook cell, even though running a package listing command in the terminal explicitly confirms the package is present. The root cause lies in the kernel specification file located in Jupyter's runtime configuration directory. The kernel configuration file contains a JSON object with an argv array specifying the exact path to the Python executable used to launch the kernel process. If this path points to a global Python binary or a deleted virtual environment path, Jupyter silently launches the wrong interpreter. To fix this failure, engineers must explicitly reinstall the kernel spec for the current virtual environment, ensuring the JSON manifest points directly to the environment's binary path. Finally, managing reproducible environments across diverse operating systems presents unique cross-platform compilation challenges. A lock file or environment file generated on a Windows development workstation may contain platform-specific build strings or Windows-only binary dependencies that fail to resolve when deployed to a Linux-based cloud server. To prevent cross-platform deployment failures, engineering teams must maintain multi-platform lock files or enforce containerized development environments where local development occurs inside a lightweight Linux container matching the production host architecture. Inspecting local will cache directories allows developers to audit precompiled binary dependencies, clearing cached wheels when troubleshooting corrupted binary builds. By isolating host operating system quirks from the development lifecycle, Engineers ensure that environment setup remains transparent, deterministic, and resilient against system-level drift. Why does a numerical array processing library like NumPy perform mathematical operations hundreds of times faster than standard Python lists? To answer this question, we must look beyond high-level syntax and explore how data is arranged in computer memory. A standard Python list is not a contiguous block of raw numerical data. It is an array of pointers pointing to scattered py-object structures in heap memory. Each floating point number in a Python list is a full-fledged object wrapper containing reference counts, type descriptors, and value payloads. When you iterate through a Python list in a loop, the CPU cannot predict which memory location will be accessed next. It experiences frequent CPU cache misses as it dereferences pointers across fragmented memory addresses, incurring massive pointer chasing overhead for every single element. Continuous contiguous memory buffers in NumPy arrays provide the mathematical foundation for hardware vectorization engines, allowing multi-core CPUs to process numerical streams at hardware limits. NumPy eliminates this pointer overhead through the n-dimensional array abstraction, known as the array. At its core, an array consists of two distinct components: a raw, contiguous block of homogeneous binary memory called the data buffer, and a lightweight Python metadata descriptor. The metadata descriptor stores essential structural information, including the data type, the shape vector defining tensor dimensions, and the strides vector controlling memory traversal. Because every element in the data buffer shares the exact same byte length and data type layout, the array does not store individual object headers or pointers. An array of 1,064-bit floating point numbers occupies exactly 8 megabytes of sequential physical RAM, allowing the CPU to read elements linearly with maximum cache line efficiency. Structured arrays and record arrays in NumPy allow developers to define heterogeneous C-style structs within contiguous memory buffers. A structured array specifies a compound data type consisting of named fields, each with its own data type and byte offset. Spatializing a structured array, imagine a continuous byte sequence where every 32-byte chunk contains a 64-bit integer ID, a 64-bit float score, and a 16-byte string label. Because structured arrays maintain fixed byte layouts, C extensions iterate through compound records using direct struct pointer dereferencing without allocating Python objects. To visualize strides and memory layout spatialization, imagine a two-dimensional grid of numbers with 4 rows and 3 columns stored in computer memory. Computer memory is fundamentally one-dimensional, a linear sequence of byte addresses. To represent a multidimensional matrix in linear memory, NumPy relies on stride calculations. To understand strides intuitively, a stride is simply the step size measured in bytes that the CPU must jump across linear physical memory to move from one array element to the next along a specific axis. In a standard row major layout known as C-contiguous order, elements within the same row are placed next to each other in memory. Moving from one column to the next requires jumping 8 bytes, assuming 64-bit floats. Moving from one row to the next requires jumping 24 bytes, the width of 3 64-bit elements. Strided array transposition mechanics rearrange axis indices in array metadata descriptors without modifying underlying memory buffers. When you transpose a matrix in NumPy, the library swaps stride values and shape dimensions in the metadata array. Transposing a C-contiguous matrix produces a Fortran contiguous array view, changing memory traversal strides without moving a single byte in physical RAM. Conversely, in a column major layout known as Fortran contiguous order, elements within the same column are stored sequentially in linear memory. Moving down a column requires an 8-byte stride, while moving across a row requires a stride equal to the column height multiplied by 8 bytes. Understanding the distinction between C-contiguous and Fortran contiguous memory is critical for numerical performance. When an algorithm accesses matrix elements in the exact order they are arranged in linear RAM, CPU hardware prefetchers automatically load upcoming memory blocks into high-speed L1 and L2 caches before the CPU even requests them. If an algorithm traverses a C-contiguous matrix column-wise instead of row-wise, it jumps across wide memory strides, causing cache line invalidations and crippling throughput. Memory alignment requirements dictate SIMD vector execution efficiency at the hardware instruction level. Modern CPU architectures require numerical memory buffers to be aligned to specific byte boundaries, such as 16-byte, 32-byte, or 64-byte boundaries, to execute vector instructions like AVX 512 or ARM Neon efficiently. Memory alignment validation using array flag descriptors checks whether data buffers satisfy hardware alignment constraints. Inspecting the aligned flag on an array verifies that its starting memory address is a multiple of the CPU's vector alignment threshold. Advanced memory stride manipulation with low-level buffer descriptors allows developers to create custom tensor views without data duplication. Inspecting array shape vectors alongside byte stride arrays reveals how NumPy maps multidimensional array coordinates down to linear memory addresses. Understanding low-level byte strides enables software engineers to optimize array traversal algorithms, maximizing CPU cache line hits, and avoiding performance penalties associated with non-contiguous memory access patterns. Strided array reinterpretation using stride_tricks as _strided enables custom sliding window extraction without data duplication. By specifying custom shape vectors and stride multipliers over an existing data buffer, developers create sliding window views that expose overlapping subarrays instantaneously. However, because as_strided bypasses array boundary checking, engineers must calculate stride offsets with mathematical precision to prevent memory segmentation faults or out-of-bounds pointer dereferences. Buffer protocol mechanics enable zero-copy data passing between C libraries and Python code. The CPython-C API exposes a low-level buffer interface called py_buffer, allowing custom C extensions, Python routines, and third-party libraries to access NumPy data buffers directly via raw memory pointers. When NumPy passes an array to an optimized C library routine, it provides a raw memory pointer address, data type identifier, and stride vector. The underlying C code accesses elements using direct C pointer arithmetic, completely bypassing Python interpreter function calls. LPAC Fortran binding interfaces provide the underlying numerical linear algebra subroutines that power NumPy matrix decompositions. Routines like gem-handle double precision general matrix multiplication, Jest computes singular value decompositions, and Jeev calculates eigenvalues. When NumPy executes matrix factorizations, it passes array pointers and leading dimension stride scalars directly into compiled LPAC Fortran routines. Low-level buffer protocol wrapping via Python and CFFI bridges the gap between high-level Python logic and custom C memory buffers. When authoring custom Python extensions for numerical algorithms, developers declare typed memory views over NumPy arrays, generating pure C pointer arithmetic loops that execute without Python interpreter overhead. Memory mapping mechanics provide a powerful mechanism for processing multi-terabyte datasets that far exceed physical RAM capacity. The memap abstraction in NumPy creates a virtual memory mapping between an array metadata descriptor and a raw binary file stored on disk. When you instantiate a memory-mapped array, the operating system does not read the entire file into physical memory. Instead, it maps file byte offsets directly into the virtual address space of the process. As your code accesses specific array slices, the operating system's virtual memory manager triggers page faults, dynamically paging required file chunks from disk into physical RAM cache. Index contraction mechanics using Einstein summation notation provide an elegant spatial abstraction for multidimensional tensor operations. The einsum function evaluates complex matrix multiplications, tensor contractions, trace evaluations, and outer products using a compact string descriptor representing array indices. Calling einsum_path on complex tensor index equations precomputes optimal matrix contraction orders, minimizing intermediate array allocations and maximizing SIMD execution speed across high-dimensional tensor contractions. Advanced universal function outer operations compute multidimensional tensor expansions across arbitrary vector inputs. Calling ufuncouter on two one-dimensional arrays evaluates pairwise binary operations across all element combinations, producing a two-dimensional matrix output without explicit loop iteration, providing a high-speed foundation for constructing pairwise distance metrics and correlation matrices directly within C loops. Slicing and array manipulation in NumPy leverage these stride mechanics to achieve zero-copy views. When you slice a subset of an array, for instance, taking every second row of a matrix, NumPy does not allocate new memory or duplicate the underlying data buffer. Instead, it creates a new metadata descriptor that points to the exact same memory address as the original array, but modifies the shape and stride attributes. Doubling the row stride tells the array descriptor to skip twice as many bytes when stepping to the next row. Because views share the underlying data buffer, mutating elements inside a slice directly alters the original array. This memory sharing architecture makes array reshaping, transposition, and slicing computationally instantaneous, requiring zero memory allocation regardless of whether the array contains 10 elements or 10 billion elements. When evaluating engineering design decisions and architectural trade-offs, vectorization stands out as the fundamental paradigm separating high-performance numerical code from scalar loop bottlenecks. Vectorization is the process of delegating element-wise mathematical operations from interpreted Python loops down to compiled C routines that execute single instruction, multiple data, SIMD, hardware instructions. In a standard Python loop, every addition requires the interpreter to check the data type of both operands, resolve method dispatch tables, create a new output PyObject wrapper, and update garbage collection reference counters. This dynamic interpretation overhead overwhelms the microsecond cost of the actual addition instruction. Vectorized execution bypasses Python interpretation entirely. When you add two NumPy arrays, the call enters a precompiled C loop that receives direct memory pointers to the raw data buffers. Modern CPU architectures feature specialized vector registers capable of holding multiple numeric values simultaneously. Using SIMD instructions like AVX, 512, or ARM Neon, a single hardware instruction adds 8 64-bit floats or 16 32-bit floats in a single clock cycle. By keeping the CPU pipeline continuously saturated with contiguous memory streams, vectorized operations achieve computational throughput approaching theoretical hardware limits. However, vectorization introduces a major architectural trade-off regarding memory consumption versus computational efficiency, particularly when working with broadcasting. Broadcasting is NumPy's mechanism for performing arithmetic operations between arrays of different shapes without incurring explicit data duplication. The broadcasting rules operate by comparing array dimension shapes from right to left. Two dimensions are compatible if they are equal, or if one of the dimensions has a size of 1. When a dimension size is 1, NumPy virtually expands that dimension to match the larger array by setting the stride along that axis to 0. A stride of 0 means that as the CPU steps through elements along that dimension, it stays fixed at the exact same memory offset, reusing a single value without allocating extra RAM. While zero-stride broadcasting provides incredible speed and zero memory overhead during arithmetic evaluation, combining broadcasting with naive intermediate operations can trigger explosive, hidden memory allocations. For example, if you compute a pairwise distance matrix between 10,000 high-dimensional feature vectors using broadcasted subtraction, NumPy dynamically evaluates an intermediate tensor with 10,000 by 10,000 entries. Even though the input arrays consume only a few megabytes, the intermediate broadcasted tensor consumes gigabytes of memory. If memory allocations exceed available physical RAM, the operating system falls back to disk swapping, reducing execution speed to a crawl. Engineers must balance the simplicity of broadcasted vectorization against chunked or iterative algorithms that bound peak memory utilization. Advanced Universal Functions, or UFuncs, provide unbuffered in-place accumulation and specialized reduction operations. Standard array operations instantiate temporary array allocations to store intermediate calculation results. Universal function methods, such as ufuncat or ufuncaccumulate, perform element-wise calculations directly into pre-allocated memory buffers without intermediate allocation overhead. Universal function reduction operations across specified axes execute high-speed tensor aggregations without intermediate memory copies. Functions like ufuncreduce compute cumulative mathematical operations, such as sum, product, maximum, or minimum, along designated array dimensions, accumulating values directly into scalar or reduced array outputs, conserving memory bandwidth during high-dimensional tensor reductions. In a production case study, consider an industrial IoT telemetry engine processing real-time sensor streams from thousands of wind turbines. Each turbine transmits high-frequency multi-axis vibration signals sampled at 10,000 Hz. The data pipeline must ingest incoming sensor arrays, remove low-frequency mechanical drift, compute running root mean square energy windows, and detect anomalous harmonic spikes within a strict 5-millisecond processing deadline per window. Initial implementations written using iterative Python list comprehensions failed catastrophically, accumulating an average latency of 200 milliseconds per sensor frame and causing message queues to back up until servers ran out of memory. The data engineering team refactored the processing pipeline to harness vectorized stride tricks and sliding window views. Instead of allocating new subarrays for every overlapping time window in the incoming vibration stream, they utilized NumPy's stride manipulation utilities to construct a sliding window view over the contiguous telemetry memory buffer. By manipulating the array strides, they generated a two-dimensional matrix view where each row represents a time-shifted window without copying a single byte of raw sensor data. They then implemented vectorized mathematical transformations across the entire windowed matrix simultaneously. Using C-compiled linear algebra routines, the pipeline calculated centered moving averages, vector-subtracted baseline mechanical drift, squared signal amplitudes, and evaluated windowed sums along designated array axes using SIMD accelerated reduction operations. By eliminating Python loop overhead and avoiding intermediate data buffer allocations, the refactored pipeline reduced per-frame processing latency from 200 milliseconds down to 0.3 milliseconds. This 600-fold throughput improvement allowed a single worker node to process incoming telemetry streams from 5,000 turbines concurrently while remaining well within strict real-time latency budgets. Troubleshooting and debugging numerical issues in NumPy requires a deep understanding of shape alignment, implicit type promotion, and memory buffer state management. One of the most common failure modes in vectorized code is shape mismatch during array broadcasting. When operating on complex multidimensional tensors, attempting to combine arrays with incompatible shapes raises a value error stating that operands could not be broadcast together. To debug these errors systematically, engineers must inspect array shape vectors from right to left, checking for missing or mismatched dimensions. Inserting explicit single-dimension axes using new axis expansion aligns matrix dimensions, allowing zero-stride broadcasting to proceed cleanly. Another insidious failure mode involves implicit data type upcasting, which silently degrades both memory efficiency and computational speed. NumPy array operations automatically promote output data types to prevent precision loss. If a high-throughput pipeline performs an element-wise operation between a 32-bit floating-point array and a single Python float scalar, which defaults to 64-bit precision in Python, NumPy silently upcasts the entire output array to 64-bit float. This unexpected upcasting instantly doubles the memory footprint of the array and degrades vectorization performance on hardware accelerators like GPUs or SIMD units optimized for single precision arithmetic. Developers should enforce explicit type parameters during array instantiation and verify array types using type properties in performance-critical sections. Memory leaks and subtle state corruption bugs frequently arise from confusing array views with deep array copies. Because slicing in array returns a view sharing the original memory buffer, modifying values in a sliced subarray permanently mutates the source dataset. If an engineering pipeline slices a subset of clean baseline data to perform experimental zero masking or normalization, and forgets that the slice is a view, the original baseline dataset becomes silently corrupted. Conversely, keeping a tiny slice of a massive original matrix alive in memory prevents the garbage collector from freeing the massive underlying data buffer, because the slice holds a reference to the entire original buffer allocation. To diagnose memory usage and array ownership, developers must check the base attribute of an array. If the base attribute is not none, the array is a view dependent on a master memory buffer. If the base attribute returns none, the array owns its memory allocation independently. When temporary slices need to persist independently without pinning massive memory buffers in heap space, calling the explicit copy method creates a brand new, detached array allocation. Finally, verifying whether an array is C-contiguous or Fortran contiguous using array flags ensures that linear algebra routines are passed memory buffers with optimal byte strides, preventing silent performance degradation in production pipelines. While NumPy provides the raw foundation for homogeneous numerical compute, real-world data science demands an abstraction capable of handling heterogeneous, tabular datasets containing numbers, strings, timestamps, and missing values. This is the domain of Pandas and its core data structures, the series and the data frame. To understand how Pandas manages complex tabular data under the hood, we must explore its internal architecture, specifically the evolution from the legacy block manager to modern column-oriented arrow backends. At a structural level, a data frame is not a simple two-dimensional array, nor is it a list of dictionaries. Historically, Pandas structured data frames using an internal component called the block manager. The block manager groups columns of identical primitive data types into consolidated two-dimensional NumPy arrays known as blocks. For instance, all 64-bit float columns are gathered into a single floating point block, all integer columns into an integer block, and all object or string columns into an object block. Alongside these data blocks, the block manager maintains an index object representing row labels and a columns index representing column headers. Spatializing this internal layout, visualize a data frame as a central metadata controller maintaining references to several distinct memory blocks. When you select a single column, Pandas locates the corresponding block within the block manager, determines the column's offset within that block, and returns a series object wrapping a one-dimensional view of that memory slice. This block consolidation strategy allowed Pandas to perform vectorized operations across multiple adjacent columns of the same data type. However, it also introduced severe architectural friction when modifying data frame schemas, adding new columns, or dealing with missing values across mixed types. Modern iterations of the library solve these historical memory inefficiencies by integrating Apache Arrow as a columnar memory backend. By setting global data type backend options to PyArrow via PD options, mode and set to Piero, data frames utilize Arrow memory buffers natively rather than legacy NumPy arrays. Unlike NumPy-backed blocks that treat string columns as arrays of Python object pointers, an Arrow-backed column stores data in a zero-copy, binary columnar format with native null bit masks. In simple terms, a null bit mask is a compact binary array of ones and zeros, where each single bit acts as a light switch flagging whether a specific row contains a valid value or a missing null. In an arrow column, contiguous memory buffers hold string bytes sequentially, while a separate bitmask array tracks precisely which rows contain valid data and which contain missing null values. Arrow string columns store variable length UTF-8 text bytes in contiguous memory buffers paired with offset arrays, replacing object pointer arrays with compact binary layouts. This columnar layout reduces string memory footprints by up to 90%, while allowing SIMD vector execution engines to perform string filtering and pattern matching directly over binary buffers. Apache Arrow dictionary encodings represent repeating string columns as compact integer key arrays referencing a single string dictionary table. Slicing an Arrow dictionary encoded column executes zero-copy pointer arithmetic, slicing the integer key array without duplicating string dictionary buffers. This dictionary encoding pattern drastically reduces memory footprints when handling high cardinality categorical data across distributed Arrow processing engines. Furthermore, Apache Arrow Inter-Process Communication, or IPC, stream serialization enables zero-copy memory sharing across separate operating system processes. Using Arrow IPC stream readers and writers, a Python process serializes data frames into contiguous binary streams that can be shared with C++, Rust, or Java applications via shared memory buffers. Receiving processes read Arrow binary streams without object deserialization or memory copying, enabling sub-millisecond data exchange between microservices. Apache Aeroflight protocols leverage gRPC transport interfaces to transfer columnar Aero data frames across distributed compute clusters with microsecond latencies. By eliminating data serialization overhead between cluster nodes, Aeroflight accelerates distributed data processing pipelines, allowing machine learning engines to ingest multi-gigabyte feature streams across distributed workers without experiencing data deserialization bottlenecks. Apache Aero record batch serialization structures tabular data into contiguous, self-describing binary chunks suitable for streaming network transport. A record batch bundles a set of equal-length Aero array vectors alongside schema metadata, enabling streaming data consumers to process incoming table chunks incrementally without waiting for full dataset downloads. Pandas extension array interfaces enable third-party libraries to define custom, high-performance data types that integrate seamlessly into data frames. By inheriting from extension array, custom data types implement array-like methods, null value handling, and typecasting contracts. Missing value representations in modern pandas use pd.na as a unified, type-agnostic missing value sentinel. Legacy pandas relied on NumPy's floating-point NaN value to represent missing data, forcing integer and Boolean columns to upcast to floating-point types whenever a missing value was present. The pd.na sentinel operates under clean three-valued logic. To explain clean three-valued logic simply, it is a logical system that admits three distinct truth values: true, false, and unknown or missing. This allows logical operations to evaluate without assuming that a missing value is automatically false. For example, evaluating true or unknown returns true regardless of the missing value. Another fundamental mechanic governing pandas' behavior is automatic index alignment. Every series and data frame possesses an explicit index object mapping row positions to unique labels. When you perform arithmetic operations or join operations between two pandas objects, execution is not determined by raw array positions. Instead, Pandas aligns data based on matching index labels. If you add two series with overlapping but non-identical row indices, Pandas performs an outer join on the indices behind the scenes. Matching index positions are summed, while non-overlapping index positions produce missing values in the resulting output. Multi-index memory spatialization represents complex hierarchical data axes through tuple keys and lexorted level arrays. A multi-index data frame maintains multiple levels of row or column labels, structuring multidimensional panel data within a two-dimensional tabular layout. To execute fast slicing operations across multi-index levels, the index must be lexically sorted using sortIndex. If a multi-index is unsorted, slicing across intermediate levels forces pandas to fall back to slow linear memory scans, raising performance warnings and degrading analytical query throughput. Modern pandas index optimization relies on range indices to minimize memory overhead. A range index represents sequential integer row indices using a lightweight start, stop, and step arithmetic tuple rather than allocating an explicit 64-bit integer array in RAM, conserving physical memory during large-scale data ingestion. Split-apply-combine mechanics govern group-by execution flows in pandas. When you invoke a group-by operation on a data frame, Pandas evaluates grouping keys using hash table aggregation or sort-based grouping. For categorical keys, Pandas constructs integer dictionary codes, mapping each unique group key to a dense hash bucket index. During the apply phase, specialized Python aggregation routines iterate over data blocks, accumulating some mean, or count statistics directly inside contiguous output buffers. Understanding hash aggregation mechanics explains why grouping by pre-encoded categorical columns executes orders of magnitude faster than grouping by unindexed raw string objects. When evaluating engineering design decisions and architectural trade-offs, developers must determine when Pandas is the optimal tool for data manipulation and when alternative engines are required. The primary constraint of Pandas is its single-threaded, eager execution model and in-memory operational pattern. Standard Pandas operations execute synchronously on a single CPU core, consuming physical memory equal to several times the raw file size of the dataset on disk. As a rule of thumb, processing a 1 GB CSV file in Pandas can easily require 5 to 10 GB of peak RAM due to temporary object instantiations, type inference overhead, and intermediate data frame copies. For datasets that fit comfortably within physical system memory, Pandas provides unparalleled ecosystem compatibility, an incredibly rich analytical API, and seamless integration with downstream machine learning frameworks like Scikit-Learn. However, when working with ultra-large datasets that exceed available RAM, or when processing pipelines require multi-core hardware scaling, continuing to rely on single-threaded in-memory Pandas creates severe production bottlenecks. In these large-scale scenarios, engineers face a strategic trade-off: adopting out-of-core lazy execution engines like Polars, Dask, or DuckDB versus optimizing Pandas through copy-on-write semantics and arrow data types. Copy-on-write represents a fundamental shift in Pandas memory management. In legacy versions of Pandas, performing operations like slicing or column filtering produced ambiguous states where a user could not predict whether the resulting data frame was a view sharing memory with the parent object or an independent copy. To prevent unintended side effects, developers frequently scattered explicit copy commands throughout their code, causing redundant memory allocations and severe performance hits. Under copy-on-write semantics, any operation that returns a subset of a data frame lazily defers memory copying. The subdata frame shares the underlying memory buffer with its parent until the user attempts to modify the data. At the exact moment a mutation is attempted, Pandas intercepts the write command, checks the block's reference count, creates an isolated copy of only the affected memory block, and applies the mutation safely without altering the parent object. This copy-on-write design prevents accidental parent data frame mutation while eliminating redundant defensive memory copies. In a production case study, consider a global e-commerce enterprise processing multi-gigabyte daily clickstream logs to train real-time product recommendation models. The raw telemetry files arrive as unorganized CSV files containing millions of event records, featuring user identifiers, session timestamps, device categories, item interaction IDs, and purchase amounts. The initial pre-processing pipeline suffered from severe memory bloat and long execution times, frequently crashing production nodes with out-of-memory errors. The data engineering team conducted an architectural audit of the pipeline and identified 3 major performance bottlenecks: inefficient object data types for low cardinality string columns, redundant memory copies during multi-step data cleaning, and slow timestamp parsing routines. They systematically re-engineered the ingestion pipeline. First, during CSV ingestion, they specified explicit arrow data types and categorical encodings for repeating string fields like device category and interaction type. Converting high cardinality object strings to categorical dictionary encodings reduced the memory footprint of those columns by over 80%. As repeating string values were replaced by compact integer keys referencing a single string dictionary. Second, they restructured data cleaning operations into a continuous method chain leveraging copy-on-write behavior. Instead of assigning intermediate data frames to temporary variables at each cleaning step, which previously triggered full block duplication, the chain applied null filtering, timestamp index alignment, string stripping, and duplicate removal lazily within unified memory blocks. Third, they replaced default Python string parsing with vectorized ISO 8601 arrow timestamp conversions, allowing the CPU to parse session date times in parallel SIMD streams. These optimizations reduced peak memory consumption from 40 gigabytes down to 6 gigabytes, while accelerating end-to-end data sanitization execution time from 45 minutes down to under 4 minutes. Troubleshooting and debugging Pandas workflows requires a clear understanding of assignment mechanics, type promotion rules, and memory fragmentation warnings. Perhaps the most infamous bug encountered by Python data engineers is the setting with copy warning. This warning occurs when an assignment is attempted on a data frame slice obtained through chained indexing. For example, filtering rows using Boolean indexing and immediately setting a column value in a secondary bracket syntax creates ambiguity for the interpreter. The first bracket evaluation returns a temporary intermediate object. Pandas cannot determine whether this intermediate object is a view or a copy. Consequently, assigning a value to it may modify the original parent data frame or modify a temporary view that is immediately discarded, leaving the original data frame unchanged. To eliminate setting with copy warning bugs deterministically, engineers must avoid chained indexing syntax entirely. Instead, use localized access methods like lock, which accepts both row conditions and column targets within a single explicit indexing call. Passing row and column selection simultaneously guarantees that Pandas evaluates the location atomically, ensuring write operations update the master data frame intent correctly. Under copy-on-write enabled environments, setting with copy warning is replaced by strict immutable assignment rules. Mutating a slice explicitly raises an exception if the user does not assign the mutated result back to a valid variable name, preventing silent bugs. Another common failure mode involves silent data type degradation to object arrays. When a numeric column containing clean integers undergoes an operation that introduces missing values, traditional NumPy-backed Pandas automatically upcasts the entire column's data type from 64-bit integer to 64-bit float, because standard NumPy integer arrays cannot represent missing NaN values. If a column contains mixed data types, such as integers and unparsable strings, Pandas silently falls back to the object data type. Object columns store raw pointers to individual Python objects, completely destroying vectorized performance and increasing memory consumption by a factor of 4. Memory profiling of data frames using deep memory inspection methods measures exact heap allocations across object columns. Calling memory usage with deep inspection forces Pandas to traverse object pointer arrays, calculating the exact byte size of every Python string object stored in memory, revealing hidden memory bloat and guiding engineers to convert high cardinality strings to compact arrow or categorical data types. To debug type promotion issues, developers should audit column data types across every stage of their data transformation pipeline using data frame info diagnostics. Implementing explicit schema validation ensures that unexpected string values or nulls do not trigger silent upcasting. Utilizing nullable integer types or arrowback data types preserves native integer types even in the presence of missing values. Furthermore, monitoring data frame performance warnings alerts engineers to memory fragmentation. Frequently inserting single columns into a large data frame causes the internal block manager to fragment into hundreds of isolated single column blocks, degrading analytical performance. Calling the copy method explicitly on a fragmented data frame consolidates disjoint memory blocks back into unified contiguous memory arrays, restoring computational throughput. Data visualization is often treated as an aesthetic art reserved for presentations, but in machine learning engineering, visualization is a fundamental diagnostic instrument. Visualizing distributions, feature correlations, and residual errors allows engineers to verify theoretical assumptions, detect hidden data corruption, and audit model behavior. However, because our masterclass is consumed through audio, we will explore visualization not by staring at rendered images, but by building a rigorous mental model of the object-oriented architecture behind plotting engines and understanding the perceptual spatialization of graphical representations. To understand how visualization libraries operate underneath the high-level API, we must unpack Matplotlib's object-oriented hierarchy. At the foundation of every Matplotlib graphic is the figure object. Spatializing this structure, visualize the figure as a blank physical canvas sitting on a drawing table. The figure does not contain data points directly. Instead, it serves as the top-level container holding layout metadata, color managers, and subcontainers. Inside the figure sits one or more axis objects. An axis object is not the plural of axis. It is a self-contained plotting area representing a coordinate system. Spatializing an axis container, imagine a bounded two-dimensional rectangle placed onto the canvas. The axis contains 2 or 3 axis objects, the x-axis, y-axis, and optional z-axis, which define data scales, tick locations, tick labels, and axis bounds called spines. Inside this coordinate system, graphic primitives such as lines, scatter points, polygons, and text labels are rendered. Surrounding the axis is a complex series of spatial coordinate transformation pipelines. Matplotlib maintains 4 distinct coordinate spaces: data coordinates, which map to raw feature values; axis coordinates, where 0 is the bottom left corner and 1 is the top right corner of the plot area; figure coordinates, spanning the entire canvas; and display coordinates, which represent actual physical pixel positions on a monitor or rendered image file. Matplotlib transform pipelines rely on 3 fundamental spatial transformation objects: ax.transdata, ax.transaxis, and figure-transfigure. The transdata transform converts raw feature coordinates directly into physical display pixels based on current axis scale limits. The transaxis transform maps relative axis coordinates, where 0 is the bottom left corner and 1 is the top right corner of the plot, to display pixels, enabling consistent text label placement regardless of data zoom levels. The transfigure transform maps relative canvas positions, providing precise spatial layout control across multi-panel figure compositions. In visual terms, an affine transformation matrix is the underlying mathematical engine that scales, shifts, and rotates raw numerical values so they land on exact pixel coordinates on your computer screen. When you issue a plotting command, Matplotlib's internal transformation matrix maps raw data coordinates down to display pixels through affine matrix transformations. For example, a data point with feature values 50 and 1000 passes through the data-to-axis transformation matrix, scaling it relative to current axis limits, and then passes through the axis-to-display matrix to calculate its exact pixel coordinate. Matplotlib's internal artist hierarchy is structured as a hierarchical tree of artist objects. Every visual element rendered on a canvas, including lines, text labels, patch shapes, axis spines, tick marks, and legend containers, inherits from the base artist class. The figure object serves as the root of the artist tree, containing axis artists, which in turn contain primitive artists like line 2D or path collection. Collection artists optimize rendering performance when displaying thousands of individual visual primitives. Standard plotting calls create an individual artist object for every single marker or line segment, creating massive memory and rendering overhead. Collection objects, such as path collection for scatter plots or line collection for multi-line charts, consolidate thousands of visual primitives into a single C-compiled graphics object. The collection artist passes a single array of coordinate offsets and color arrays to the low-level rendering backend, drawing millions of data points in a single vector rendering pass. Rendering backend mechanics dictate how vector drawing commands are translated into physical output formats. Matplotlib separates drawing logic into front-end artists and back-end renderers. GUI backends, such as Qt and TK, render interactive window displays, managing operating system event loops for panning and zooming. Non-interactive raster backends, such as AG, translate drawing primitives into fixed pixel grids via anti-grain geometry C++ engines, exporting high-density PNG or JPEG raster images. Non-interactive vector backends, such as PDF and SVG, preserve mathematical line and curve paths as resolution-independent vector instructions, ensuring scientific figures remain crisp when printed or scaled in publication documents. Matplotlib font fallback and glyph rendering engines process Unicode text rendering across diverse language character sets. When rendering mathematical symbols or non-Latin typography on graphic canvases, Matplotlib's font manager evaluates system font directories, falling back to sticks or computer modern font packages to ensure mathematical equations render with publication quality layout precision. Seaborn facet grid and pair grid containers spatialize multivariable relationships across grid layouts. A facet grid maps subsets of a data frame across a two-dimensional grid of Matplotlib axes based on categorical feature levels. The container manages axis limit synchronization across subplots automatically, ensuring comparative statistical distributions maintain identical spatial scales across visual panels. Seaborn builds directly on top of this object-oriented foundation, acting as a high-level statistical visualization abstraction layer. While Matplotlib requires developers to manually compute histograms, kernel density estimates, or categorical groupings before drawing graphic primitives, Seaborn accepts raw Pandas data frames, performs statistical aggregation under the hood, and automatically populates Matplotlib axis objects with perceptually optimized graphic elements. Moving to engineering design decisions and architectural trade-offs, developers must choose between Matplotlib's explicit object-oriented API and its implicit state machine interface, known as Pyplot. The Pyplot interface mimics legacy matrix environments, maintaining a hidden global state that tracks the currently active figure and active axis. When you call simple plotting functions without instantiating explicit objects, Pyplot implicitly routes drawing commands to whatever figure was modified last. While the State Machine API is convenient for quick interactive exploration in disposable notebook cells, relying on implicit global state in production software introduces severe architecture smells and race conditions. In automated data pipelines or multi-threaded server applications, multiple worker threads invoking implicit Pyplot commands will overwrite each other's global figure state, causing plots to draw onto wrong canvases or corrupting rendered assets. Modern engineering best practices demand strict adherence to the explicit object-oriented API. Engineers explicitly instantiate figure and axis objects using factory methods, passing the specific axis reference into plotting functions. This functional, object-passing pattern guarantees thread safety, isolates graphic state, and makes visual generation fully modular and testable. Another vital design trade-off involves perceptual color science and graphic cognitive load. A common mistake in scientific visualization is using rainbow or jet color maps, where hues cycle rapidly across spectrums. Human visual perception does not perceive changes in color hue linearly. Bright yellow appears perceptually much brighter than cyan or red, even if they represent equal mathematical steps along a continuous numerical scale. This non-monotonic perceptual luminance creates artificial visual boundaries, misleading the viewer into perceiving sharp transitions where data distributions are actually smooth. Engineers must select perceptually uniform color maps, such as Voridus, Plasma, or Civitas. Perceptually uniform color map design guarantees that continuous visual lightness gradients map directly to numerical feature changes. Selecting uniform color maps prevents artificial visual boundary distortions, ensuring diagnostic charts present feature distributions accurately for all audience members. Perceptual color space conversions rely on standardized color appearance models like CAM02 UCS. Unlike RGB or HSV color spaces, which reflect hardware display mechanics rather than human vision, CAM02 UCS models human visual perception linearly, measuring perceptual color differences using uniform Euclidean distances. Color maps built in uniform perceptual spaces guarantee that numerical feature deltas correspond directly to perceptual lightness deltas. Color appearance models in scientific visualization evaluate perceptual color differences using uniform color spaces, projecting continuous numerical feature values into visually uniform color maps. Furthermore, color maps must accommodate color vision deficiencies by ensuring monotonic lightness gradients from dark to light. Color vision deficiency simulation algorithms test graphic legibility across deuteranopia, protanopia, and tritanopia color blindness conditions. To clarify these conditions simply, deuteranopia represents green blindness, protanopia represents red blindness, and tritanopia represents blue blindness. Simulation models apply color transformation matrices to RGB values, projecting colors into perceived visual spaces for color-deficient viewers. Graphic contrast ratios and accessibility design standards ensure visual data representations remain readable for all viewers, conforming to web content accessibility guidelines. Selecting high-contrast color palettes and distinct marker shapes ensures diagnostic plots remain legibly distinct across different monitor displays and printed reports. When designing diagnostic charts, minimizing chart junk, such as heavy background grid lines, redundant borders, and non-informative decorative gradients, reduces cognitive overhead. Aligning visual ink directly to data representation maximizes the data-to-ink ratio, ensuring diagnostic figures communicate statistical signals with maximum perceptual clarity. Matplotlib event callback interfaces enable custom interactive diagnostic tools. Using the MPL_connect method, developers register custom Python callback functions that listen for mouse clicks, key presses, or axis resize events on rendered figure canvases, allowing engineers to build custom interactive visual inspection tools within interactive development sessions. In a production case study, consider an autonomous machine learning infrastructure platform running continuous model validation in a financial fraud detection pipeline. Every hour, thousands of incoming transaction batches pass through deployed classification models. The platform requires an automated diagnostic reporting engine that evaluates incoming feature distributions against baseline training distributions, generates visual drift reports, renders confusion matrices, and exports static graphical artifacts to cloud storage for compliance auditing. The engineering team designed a headless visual generation service using Matplotlib's non-interactive AG rendering backend. Because the server environment runs inside a headless Linux container without a display server or graphical windowing system, attempting to initialize default GUI backends would cause the application to crash instantly. By forcing the rendering backend to AG, the service routes drawing instructions directly to an in-memory raster graphics buffer, executing pure C++ pixel rendering via the anti-grain geometry library without requiring system display drivers. The reporting engine accepts normalized statistical summaries from feature drift detectors. Using the explicit object-oriented API, the service constructs a multi-panel diagnostic figure. Panel 1 renders paired kernel density estimates comparing incoming transaction amounts against baseline training distributions using perceptually uniform translucent fills. Panel 2 renders a normalized confusion matrix heat map using explicit color bar scales. Panel 3 displays a receiver operating characteristic curve with annotated area under curve confidence intervals. The rendering service serializes the figure directly into a high-density PNG byte stream, transmitting the graphic to object storage without writing temporary files to disk. This headless, thread-safe service processes hundreds of model diagnostic reports per minute, providing fully automated compliance documentation. Troubleshooting and debugging visualization systems requires mastering back-end configuration, figure lifecycle memory management, and layout spatial adjustments. The single most catastrophic failure mode in automated plotting pipelines is figure memory leakage. In Matplotlib, calling plot functions or instantiating figures creates a persistent reference inside the global pyplot state tracker. If a data pipeline loops over thousands of dataset chunks, generating a diagnostic plot for each chunk without explicitly closing the figure, Matplotlib retains every figure object in heap RAM. Over time, physical memory consumption escalates linearly until the operating system terminates the Python process with an out-of-memory error. To eliminate figure memory leaks, developers must manage figure life cycles explicitly. After rendering and saving a graphic asset or extracting its byte stream, engineers must invoke the explicit close method on the figure or wrap figure creation inside context managers. Calling figure close instructs Matplotlib to purge the figure's internal graphics buffer, release its transformation matrices, and remove all references from global state trackers, allowing Python's garbage collector to reclaim memory immediately. Another frequent failure mode involves label clipping and text overlapping in multi-panel figures. When rendering multi-axis subplots with long feature names or rotated tick labels, Matplotlib's default fixed spacing often causes axis titles, tick text, and legend boxes to collide or get sliced off at the figure boundaries. This occurs because default spatial margins allocate fixed pixel distances regardless of text label lengths. To resolve layout collisions automatically, developers should activate tight layout algorithms or constrained layout engines. Matplotlib's tight layout engine calculates exact bounding boxes for all text elements, legends, and subplots using display coordinate transformations. During layout adjustment, the engine evaluates text label extent rectangles, dynamically expanding margin padding to prevent title clipping or tick label overlap. Constrained layout extends tight layout by updating spatial bounds iteratively during rendering, ensuring complex multi-panel figure layouts remain perfectly aligned. Finally, debugging color bar scaling mismatches and dynamic axis limits prevents misleading diagnostic interpretations. When generating comparative heat maps across different data batches, Matplotlib automatically scales each color bar to the minimum and maximum values present in that specific batch. If batch A ranges from 0 to 10 and batch B ranges from 0 to 100, identical color shades across the two plots will represent completely different numerical magnitudes, destroying visual comparability. Engineers must enforce explicit, fixed color normalization bounds across comparative plots, guaranteeing that perceptual color shades map to absolute, identical numerical values across all generated diagnostic reports. With environment isolation, array computation, data wrangling, and diagnostic plotting established, we now turn to the cornerstone framework of classical machine learning in Python, Scikit-Learn. Scikit-Learn's widespread adoption across industry and academia is not merely a historical accident. It is the direct result of an exceptionally clean, consistent, and object-oriented API design. At the core of Scikit-Learn's design philosophy is the estimator interface. An estimator is any object that learns state from data. Whether you are instantiating a simple mean imputer, a standard feature scaler, a principal component analysis transformer, or a complex random forest classifier, every single algorithm implements the exact same fundamental interface lifecycle. This unified contract is organized around three primary operations: the fit method, the transform method, and the predict method. Scikit-Learn's estimator class architecture relies on object-oriented inheritance from fundamental mixin classes: base estimator, transformer mixin, classifier mixin, and regressor mixin. Base estimator provides built-in parameter inspection and serialization capabilities, implementing get_params and set_params methods that inspect object constructor signatures dynamically. Transformer mixin automatically provides fit_transform functionality by combining fit and transform calls in a standardized default implementation. Classifier mixin and regressor mixin append score evaluation methods, computing mean accuracy or coefficient of determination metrics directly from feature matrices and target vectors. Spatializing this object lifecycle, imagine an estimator as a state machine that transitions from an uninitialized, stateless configuration object into a fully learned, state-bearing model object. When you instantiate an estimator, you pass high-level hyperparameters, such as regularization strengths, tree depths, or distance metrics, into the object's constructor. At this stage, the estimator contains configuration parameters, but possesses zero knowledge about specific datasets. It holds no learned numerical weights, internal offsets, or statistical summaries. State acquisition occurs exclusively when you invoke the fit method, passing in a feature matrix X and an optional target vector Y. Upon calling fit, the estimator analyzes the input data, estimates underlying statistical parameters, and attaches those learned parameters to the object instance. Crucially, Scikit-Learn enforces a strict naming convention to distinguish user-configured hyperparameters from parameters learned during fitting. Any attribute estimated during the fit call is stored with a trailing underscore suffix. For example, a scaling estimator stores learned feature means in an attribute named mean underscore and learned standard deviations in scale underscore. If an object attribute lacks a trailing underscore, it represents a hyperparameter configured prior to fitting. The distinction between transformers and predictors further refines this API hierarchy. A transformer is an estimator that implements the transform method, accepting a feature matrix X and returning a modified, transformed feature matrix. Transformers are used for data preprocessing, scaling, encoding, missing value imputation, and dimensionality reduction. To optimize computational efficiency during training, transformers also implement a combined fit_transform method, which computes learned parameters and applies the transformation in a single optimized pass. Conversely, a predictor is an estimator that implements the predict method, accepting a feature matrix X and returning target predictions, such as class labels or continuous target values. Model cloning mechanics via the clone function enable clean hyperparameter duplication without copying learned statistical state. When hyperparameter optimization algorithms or cross-validation routines evaluate an estimator across multiple data folds, they call clone on the master estimator object. The clone function inspects constructor parameters, instantiating a fresh estimator instance with identical configuration hyperparameters, but with zero learned trailing underscore attributes. This guarantees that each cross-validation fold trains an isolated model instance, eliminating state leakage across cross-validation splits. Feature name propagation APIs enhance schema visibility across multi-step pipeline transformations. By implementing get_feature_names_out methods, custom and built-in transformers track feature column names dynamically as data passes through scaling, encoding, and selection steps. Metadata parameter routing protocols introduced in modern versions provide explicit control over how metadata parameters, such as sample weights, groups, and scoring parameters, are routed through composite pipelines. Using functions like set_fit_request or set_transform_request, developers specify which pipeline transformers or estimators require sample weight metadata during fitting or transformation. Multi-output estimator interfaces extend Scikit-Learn estimators to handle target matrices containing multiple target columns simultaneously, streamlining multi-target forecasting workflows. Estimator score methods evaluate model performance against standard validation metrics. For classification estimators, score calculates mean accuracy. For regression estimators, score returns the coefficient of determination R² metric. Scikit-Learn estimator metadata inspectability relies on get_params and set_params parameter routing algorithms. Calling get_params on a composite estimator inspects constructor signatures recursively, returning a nested dictionary of hyperparameter values. Calling set_params updates hyperparameter values dynamically without reinstantiating object references, enabling automated hyperparameter search routines to alter model configurations cleanly during iterative validation sweeps. Estimator frozen state inspection utilities verify model immutability prior to deployment. Inspecting estimators using validation routines confirms that trailing underscore parameters remain unmutated during prediction passes. Enforcing strict read-only access to fitted estimator attributes during serving prevents concurrent inference threads from altering model decision boundaries in production microservices. Scikit-Learn parameter validation frameworks enforce strict type and boundary checking across estimator constructor arguments. Functions like validate_params verify that hyperparameter values satisfy specified numerical ranges or valid string options before model fitting begins, raising clear exceptions early to prevent invalid parameter combinations from executing inside low-level C routines. Scikit-Learn estimator class inheritance structure separates stateless configuration parameters from stateful fitted parameters. Storing learned statistics in trailing underscore attributes guarantees clear state visibility, enabling hyperparameter optimization routines and model cloning functions to duplicate estimators deterministically. Moving from mechanics to engineering design decisions, architects must weigh the trade-offs of Scikit-Learn's stateful object paradigm against pure functional programming alternatives. In a stateful object model, the estimator instance encapsulates both the transformation logic and the learned mathematical state. This encapsulation makes pipeline composition exceptionally elegant. A complex workflow chaining 20 preprocessing steps and a final classifier can be serialized as a single composite object. However, stateful objects require careful state management in production systems. If an estimator instance is accidentally refitted on a secondary dataset in a server handler, its internal trailing underscore attributes are overwritten in place, corrupting the model's production state. Another key design trade-off involves input-output data container contracts. Historically, Scikit-Learn mandated that all feature matrices be converted into raw, two-dimensional NumPy wind arrays. Passing a Pandas data frame into a fit or transform call stripped away column names and index labels, returning a plain numerical matrix. While this guaranteed maximum memory efficiency and linear algebra execution speed, it introduced significant friction when managing tabular datasets with heterogeneous column types, making feature tracking prone to index shifting errors. Modern Scikit-Learn architectures address this trade-off by offering configurable set output APIs. Calling set_config with transform_output set to Pandas instructs all fitted transformers to return Pandas data frames natively, preserving column names and index labels across transformation pipelines without requiring explicit per-transformer configuration. By enabling data frame output configurations, estimators dynamically preserve Pandas data frame or Apache Arrow data frame metadata across transform calls. When a transformer processes an input data frame, it returns an output data frame with preserved column names and index alignment, rather than a raw NumPy array. This hybrid approach retains Scikit-Learn's high-speed linear algebra execution while dramatically improving code readability, schema validation, and feature lineage tracking across complex data transformation workflows. In a production case study, consider a high-throughput financial fraud scoring engine deployed as a microservice inside a containerized cloud cluster. The microservice ingests real-time credit card transaction payloads serialized as JSON streams. To evaluate transaction risk within a 20-millisecond service level agreement, the service must pass incoming feature vectors through a pre-trained feature scaling estimator, an imputer transformer, a categorical encoder, and a gradient-boosted decision tree classifier. The engineering team established a strict separation between offline training and online inference lifecycles. During offline training, a batch pipeline executes model fitting against historical transaction datasets, optimizing hyperparameters and fitting all pre-processing transformers. Once fitting completes, the entire composite model object, containing all fitted transformers and the final predictor, is serialized into a binary stream using high-speed serialization protocols and uploaded to an immutable artifact repository. During online inference, the microservice initializes an isolated execution container. Upon container startup, a warm-up routine downloads the serialized model artifact from object storage, deserializes the composite object into memory, and verifies its trailing underscore state attributes. When a real-time transaction payload arrives over a network socket, The handler passes the feature matrix directly to the prefitted pipeline's predict method. Because the online container invokes only transform and predict operations, never invoking fit, the microservice executes pure matrix multiplication and tree traversals without allocating state memory. This architectural isolation guarantees thread safety, eliminates runtime fitting overhead, and allows a single service container to score over 5,000 transactions per second within a sub-10 millisecond latency envelope. Troubleshooting and debugging Scikit-Learn API workflows requires a thorough understanding of state exceptions, dimensionality requirements, and sparse matrix representations. One of the most ubiquitous runtime errors encountered in production is the not fitted error. State verification via check_is_fitted guarantees that estimators possess learn trailing underscore parameters before executing transform or predict calls. When transform is invoked, check_is_fitted checks for the existence of fitted attributes like mean underscore or coef underscore. If these attributes are missing, the utility raises a not fitted error. Debugging a not fitted error requires auditing execution order in your application logic, ensuring that model initialization and parameter fitting precede any downstream inference calls. Scikit-Learn input validation utilities enforce strict array shape and data type contracts prior to model fitting. Internal functions like check_array and check_consistent_length inspect input matrices X and target vectors Y, verifying that matrices contain no infinite values or unexpected NaN entries, converting inputs to contiguous number PY or SciPy sparse arrays, and validating sample count consistency across inputs. If input dimensions violate estimator requirements, validation functions raise informative exceptions before execution enters low-level C routines. A secondary failure mode involves matrix dimensionality mismatches between feature matrices X and target vectors Y. Scikit-Learn estimators enforce strict array shape contracts. The feature matrix X must strictly be a two-dimensional array structure where rows correspond to individual samples and columns correspond to distinct features. Passing a one-dimensional array containing 10,000 numbers as feature matrix X causes Scikit-Learn to raise a value error expecting a two-dimensional matrix with explicit sample and feature axes. Conversely, the target vector Y is expected to be a one-dimensional array of target values. Passing a two-dimensional column vector for Y often raises shape warnings or causes implicit array flattening, degrading training performance. Memory blowups frequently occur when transformers operate on high cardinality categorical data, converting sparse data representations into dense number PY matrices. When transforming categorical text features or high cardinality categorical identifiers using one-hot encoding, Scikit-Learn by default returns a SciPy sparse matrix. A sparse matrix stores only non-zero values and their corresponding coordinate indices in memory, consuming a tiny fraction of the memory required by a dense matrix filled with zeros. If a developer explicitly forces sparse output matrices into dense number PY arrays using array conversion calls, a feature matrix with millions of zero entries will instantly consume tens of gigabytes of RAM, causing memory allocation crashes. To debug memory bloat and sparse matrix conversions, developers should inspect matrix types using Scikit-Learn's internal inspection utilities. Preserving sparse matrix outputs throughout preprocessing transformers ensures that high-dimensional categorical features remain in memory-efficient compressed sparse row formats until handed off to downstream solvers optimized for sparse inputs. Finally, verifying hyperparameter parameter types using estimator inspection tools prevents silent parameter mismatches, guaranteeing that estimators execute deterministically across diverse execution environments. Raw real-world features rarely arrive in a mathematical format ready for model training. Numerical attributes often span vastly different orders of magnitude, ranging from individual age counts to multimillion-dollar transaction amounts. Categorical variables enter pipelines as arbitrary text strings or discrete status codes. If passed directly to optimization algorithms, features with larger numerical scales will dominate gradient calculations or distance metrics, starving smaller scale features of predictive influence. Data preprocessing, encompassing feature scaling, categorical encoding, and vector normalization, is the critical engineering discipline that transforms raw, heterogeneous inputs into numerically stable, well-conditioned feature spaces. To understand feature scaling mechanics, we must examine the mathematical geometry of feature spaces and contrast three primary scaling transformations: standardization, min-max scaling, and robust scaling. Standardization, implemented via standard scaling transformers, shifts and rescales numerical distributions to achieve zero mean and unit variance. Mathematically, for each feature value, the transformer subtracts the empirical feature mean and divides by the empirical standard deviation. Spatializing this transformation, visualize a multidimensional cloud of data points floating in space. Standard scaling translates the center of gravity of the data cloud to the origin of the coordinate space, and rescales the cloud along each axis so that one standard deviation along any feature axis corresponds to a spatial distance of exactly 1 unit. Min-max scaling applies a linear projection that bounds feature values within a fixed numerical range, typically between 0 and 1. The transformer computes the feature minimum and maximum across the training set, subtracting the minimum from each value and dividing by the feature range. Min-max scaling compresses feature distributions into a hypercube bounded by 0 and 1. While bounded scaling is required for algorithms that expect non-negative inputs or explicit boundary limits, such as neural network input layers or image processing pipelines, it is extremely sensitive to extreme values. A single catastrophic outlier with an artificially high magnitude will squash the vast majority of valid data points into a microscopic cluster near zero. Robust scaling mitigates outlier sensitivity by anchoring transformations to non-parametric order statistics rather than parametric means and variances. Robust scaling transformers compute the median and the interquartile range, the distance between the 25th percentile and the 75th percentile. For each value, the transformer subtracts the median and divides by the interquartile range. Because medians and interquartile ranges are governed by percentile positions rather than extreme value magnitudes, robust scaling centers and scales the core bulk of the distribution without allowing far-flung outliers to distort the central scaling parameters. Vector normalization diverges fundamentally from feature scaling. While feature scaling transforms values vertically down columns across samples, vector normalization transforms values horizontally across features within an individual sample. Normalization scales sample feature vectors to have a unit norm, typically using the L1 norm or L2 norm. In L1 normalization, feature values are divided by the sum of their absolute values, ensuring that the elements of each sample vector sum to 1. In L2 normalization, feature values are divided by the Euclidean length of the vector, projecting every sample vector onto a unit hypersphere. Normalization is essential in text classification and clustering applications where the directional orientation of a feature vector matters more than its raw magnitude. Categorical encoding bridges the gap between discrete non-numeric attributes and numerical linear algebra solvers. One hot encoding converts a categorical variable with k distinct categories into k binary indicator columns. For any given sample, exactly one binary column receives a value of 1, indicating the active category, while all remaining k-1 columns receive 0. Spatializing one-hot encoding, visualize mapping discrete text labels into orthogonal coordinate axes. However, when dealing with high cardinality categories containing thousands of unique values, one-hot encoding triggers a massive expansion in feature matrix width. To prevent memory exhaustion, one-hot encoders output compressed sparse matrix structures, where 0 entries consume no physical storage space. Rare category handling in one-hot encoders using min_frequency hyperparameters prevents sparse feature matrix explosion. When min_frequency is specified as an integer sample threshold or fractional percentage, categories with occurrences below the threshold are automatically grouped into a single combined rare category column, bounding feature matrix width while retaining statistical representation for infrequent categories. Sparse matrix coordinate COO format represents sparse data using 3 simple one-dimensional arrays: row indices, column indices, and numerical values. While COO format is inefficient for arithmetic matrix operations or row slicing, it is exceptionally fast for incrementally constructing sparse matrices from raw data streams. Once sparse data collection completes, converting a COO matrix to compressed sparse row CSR or compressed sparse column CSC format organizes indices for high-speed linear algebra execution. Compressed sparse row or CSR matrix mechanics optimize sparse feature storage for high cardinality encodings. A CSR matrix represents a sparse two-dimensional array using 3 contiguous one-dimensional arrays: a data array holding non-zero values, a column indices array storing feature column positions, and a row pointers array tracking byte offsets for each row. A CSR matrix with m rows contains an m+1 length row pointer array. The number of non-zero entries in row I is calculated directly as row pointer I plus 1 minus row pointer I. This offset indexing enables O of one row access, making CSR matrices ideal for fast row-wise matrix vector multiplications. Compressed sparse column, or CSC, matrix representations complement CSR formats by optimizing column-wise operations. A CSC matrix stores non-zero values alongside row indices and column pointer offsets, enabling O of one column slicing and fast column-wise matrix multiplications, allowing univariate feature selection transformers to achieve optimal cache locality. Ordinal encoding maps discrete categories to sequential integer keys. While ordinal encoding is mathematically appropriate for ordered categories, such as low, medium, and high risk levels, applying integer ordinal keys to nominal, unordered categories introduces a dangerous architectural defect. Linear models and distance-based algorithms will interpret integer keys as meaningful quantitative distances, incorrectly assuming that category index 3 is 3 times greater than category index 1. Empirical Bayes target encoding incorporates global prior statistics to regularize categorical target encoding in low sample levels. To understand this concept simply, when a category level appears only once or twice in your dataset, computing its target mean creates a noisy estimate. Empirical Bayes pulls that small sample estimate toward the overall dataset average, balancing local category variance against population expectations to prevent rare categorical levels from introducing high variance into downstream linear models. Empirical Bayes target encoding regularizes categorical target means using a smoothing weight formula. S underscore I equals N underscore I times Y underscore bar underscore I plus M times Y underscore bar, divided by N underscore I plus M, where N underscore I is the category sample count, Y underscore bar underscore I is the category target mean, M is the smoothing weight hyperparameter, and Y underscore bar is the overall global target mean. When category sample count N underscore I is large, the local category mean dominates the encoding. When N underscore I is small, the global target mean pulls the encoding toward baseline prior expectations, preventing rare categories from introducing extreme variance into model features. Quantile transformation applies a non-parametric mapping that maps feature distributions to uniform or normal output distributions. Implemented via quantile transformer, this transformation estimates the empirical cumulative distribution function of a feature across training samples. Quantile transformer non-parametric mapping fits empirical cumulative distribution functions by sorting training sample values and computing percentile ranks. It maps feature values to their corresponding percentile ranks, transforming arbitrary skewed, bimodal, or heavy-tailed distributions into smooth uniform distributions bounded between 0 and 1, or transforms them into Gaussian normal bell curves using the inverse normal cumulative distribution function. Unlike linear scaling, quantile transformer is entirely nonlinear, reducing the impact of extreme outliers while expanding spatial resolution in dense data regions. Quantile transformer subsampling strategies bound memory overhead during large-scale empirical CDF estimation. When fitting quantile transformers on massive datasets containing millions of rows, specifying the subsample hyperparameter restricts empirical quantile calculation to a random subset of samples, accelerating fitting execution speed dramatically while estimating continuous cumulative distribution curves with high statistical fidelity. When evaluating engineering design decisions and architectural trade-offs, developers must analyze the systemic impact of scaling and encoding choices on downstream model performance and memory utilization. The primary trade-off in categorical encoding exists between the spatial sparse matrix representation of one-hot encoding and high-level target encoding. Target encoding replaces each categorical level with the expected mean of the target variable for that category. Target encoding preserves matrix width by representing a categorical attribute as a single continuous numerical column, completely bypassing sparse matrix memory overhead. However, target encoding introduces a severe architectural risk: target leakage. If target statistics are computed naively across the entire dataset, the encoder injects future target information directly into training features, leading to severe overfitting where the model achieves artificially perfect performance during training but fails catastrophically on unseen validation data. To mitigate target leakage, engineers must employ out-of-fold target encoding with smoothing regularization, or stick with sparse one-hot encoders when categorical cardinality remains manageable. Another crucial design trade-off revolves around choosing between standard scalar and robust scalar in high-throughput feature pipelines. If a dataset adheres strictly to Gaussian distributions without extreme values, standard scalar produces optimal conditioning for linear models and principal component analysis. But in real-world telemetry, web clickstreams, and financial markets, feature distributions display heavy-tailed power law distributions filled with legitimate extreme values. Applying standard scalar to heavy-tailed distributions results in near-zero standard deviations for the bulk of samples, distorting gradient updates. Robust scalar provides architectural stability under heavy-tailed distributions, maintaining consistent feature scaling even when upstream data sources experience temporary variance spikes. In a production case study, Consider a global credit risk scoring system evaluating incoming credit applications in time. The applicant stream contains continuous features, such as annual income, credit utilization ratios, and debt service coverage, alongside high cardinality categorical features like employment industry codes and geographic zip codes. The pre-processing pipeline must process incoming application payloads, apply learned scaling and encoding transformations, and pass clean feature vectors to a risk assessment model within a strict 15-millisecond response window. The engineering team encountered major production failures when deploying an unconstrained pre-processing setup. During initial rollouts, the online inference service used a one-hot encoder fitted on historical training data. When a new credit application arrived containing an unseen geographic zip code that did not exist in the historical training set, the default one-hot encoder threw an unhandled value error for unknown categories, crashing the inference worker process. Furthermore, applicant income features exhibited massive extreme values, causing standard scalars to squash normal income values into zero-variance bins. To build a resilient production pipeline, the team re-engineered their pre-processing architecture. First, they configured the one-hot encoder with explicit unknown handling parameters, setting handle_unknown to ignore. When the inference service encounters an unseen zip code or industry level during online scoring, the encoder silently sets all binary indicator columns for that categorical feature to 0, preserving vector dimensionality without throwing runtime exceptions. Second, they replaced standard scalar with robust scalar across all financial income and balance attributes, ensuring that ultra-high income outlier applications no longer distorted scaling medians for standard applicants. Third, they wrapped all scaling, encoding, and normalization transformers inside a unified Scikit-Learn pipeline object, serializing the fitted pipeline as a frozen binary artifact. This robust architecture eliminated runtime crash exceptions, handled out-of-vocabulary categories gracefully, and maintained sub-8 millisecond scoring latencies under heavy production traffic. Troubleshooting and debugging data pre-processing systems require strict vigilance against data leakage, division by zero anomalies, and sparse matrix serialization traps. Data leakage occurs when statistics from validation or test datasets contaminate the fitting phase of pre-processing transformers. A common engineering mistake is calling fit or fit_transform on the full dataset prior to executing train test splits or cross-validation folds. When a scalar or imputer computes feature means variances or missing value baselines across the complete dataset, information from the test set leaks directly into the training features. Downstream cross-validation metrics become overly optimistic, masking generalization failures that will inevitably erupt when the model encounters true out-of-sample data. To prevent data leakage deterministically, engineers must enforce a strict structural boundary. Transformers must be fitted exclusively on training data folds. Once an imputer or scalar learns parameters from the training fold, its transform method is invoked independently on validation folds, test sets, and production inference streams. This structural separation guarantees that test sets remain completely unseen, providing an uncorrupted benchmark of model generalization performance. Another frequent failure mode involves zero-variance division by zero in standard scalar. If a numerical figure in the training set contains constant values across all rows, its sample standard deviation evaluates to 0. When standard scalar attempts to divide feature residuals by standard deviation, the mathematical operation produces float division by 0, filling the feature matrix with infinite values or NaN entries. Downstream linear models or gradient descent optimizers receiving infinite inputs crash or output NaN prediction weights. To debug zero-variance bugs, developers should run variance threshold filters prior to scaling, dropping constant features from the feature matrix automatically. Finally, managing memory consumption during high cardinality one-hot encoding requires inspecting sparse matrix storage formats. Passing a high cardinality feature into a one-hot encoder configured to output dense NumPy arrays will attempt to allocate terabytes of RAM, triggering host operating system memory kills. Engineers must verify that one-hot encoders retain sparse matrix outputs, passing compressed sparse row matrices directly to downstream algorithms capable of consuming sparse inputs without dense memory expansion. In real-world data engineering pipelines, missing observations and anomalous outliers are not rare edge cases. They are systemic realities. Telemetry sensors drop connections, survey respondents skip sensitive questions, database migrations leave orphan records, and system faults inject garbage readings into data streams. If left unaddressed, missing values crash downstream numerical algorithms, while unhandled outliers distort statistical parameter estimation, pulling decision boundaries away from optimal generalization space. Robust machine learning architectures demand a formal, mathematically grounded methodology for detecting, imputing, and bounding incomplete or corrupt data. To understand missing data mechanics, we must first categorize missingness mechanisms into three distinct theoretical regimes: missing completely at random, missing at random, and missing not at random. Missing completely at random occurs when the probability of a value being missing is entirely independent of both observed variables and unobserved missing values. For instance, if a network packet drops purely due to random electrical noise, the missingness injects no systematic bias into the dataset. Under this regime, deleting rows with missing values reduces sample size and statistical power, but does not introduce statistical estimation bias. Missing at random occurs when the probability of missingness depends systematically on other observed variables in the dataset, but is independent of the missing value itself. For example, if older patients in a medical study are less likely to report income levels, missingness in the income feature is systematically related to the observed age feature. If an engineer naively drops rows with missing income, the pipeline selectively purges older demographic samples, severely biasing downstream clinical models. Missing not at random represents the most challenging regime, where the probability of missingness depends directly on the unobserved value itself. For example, individuals with extremely high incomes or severe depression symptoms may actively decline to disclose those metrics. In this scenario, missingness itself carries predictive information. Imputing missing values under missing not at random without adding missingness indicator flags obscures crucial behavioral signals from downstream estimators. Univariate imputation, implemented via simple imputer transformers, fills missing values in a target feature using summary statistics computed along that column independently. Mean imputation replaces missing values with the arithmetic mean of observed samples, while median imputation uses the median, providing robust central tendency estimation under skewed distributions. Constant imputation replaces missing values with a fixed placeholder value, such as -999, which is frequently paired with missing indicator transformers. A missing indicator transformer appends a binary column to the feature matrix, where a value of 1 explicitly flags that an observation was originally missing. Multivariate imputation models missing values as a function of all other available features in the matrix. K-nearest neighbors imputation, or KNN imputer, spatializes feature relationships by finding the K most similar samples in multidimensional space based on Euclidean distance across observed coordinates. The missing value is then computed as a weighted average of those K nearest neighbors. Iterative imputation, operating via chained equations, treats every feature with missing values as a target variable in a sequential regression problem. Multivariate imputation by chained equations, or MICE, operates through an iterative sequence of univariate regression models. In simple terms, MICE treats each missing feature as a target variable, training regression models over observed features to fill missing entries iteratively until imputed values stabilize across the dataset. Outlier detection mechanics identify observations that deviate so significantly from the surrounding data distribution that they suggest a different underlying generative mechanism. Non-parametric univariate bounds rely on the interquartile range rule, defining any data point falling beyond 1.5 times the interquartile range above the third quartile or below the first quartile as a potential outlier. Mahalanobis distance accounts for multivariate feature covariance when identifying spatial outliers. The Mahalanobis distance equation evaluates the square root of the transposed feature residual vector multiplied by the inverse covariance matrix, multiplied by the feature residual vector. By scaling feature distances by the inverse covariance matrix, Mahalanobis distance measures spatial deviations along principal variance axes, correctly identifying outliers in correlated multidimensional feature spaces where Euclidean distance metrics fail. Covariance matrix singularity in Mahalanobis distance calculations occurs when feature columns are perfectly collinear. When a covariance matrix is singular, its determinant evaluates to 0, preventing standard matrix inversion. To resolve singular covariance matrices, developers compute the Moore-Penrose pseudo-inverse or apply shrinkage covariance estimators, stabilizing Mahalanobis distance calculations in high-dimensional collinear feature spaces. Mahalanobis distance thresholding relies on chi-square distribution quantile values to flag multivariate outliers. In a d-dimensional feature space, squared Mahalanobis distances follow a chi-square distribution with d degrees of freedom, flagging points exceeding critical chi-square thresholds as statistically significant multivariate outliers. Isolation Forest is a powerful tree-based ensemble algorithm designed explicitly for high-dimensional multivariate outlier detection. Rather than profiling dense normal data regions, Isolation Forest explicitly isolates anomalies. Spatializing an isolation forest, imagine recursively partitioning feature space using random hyperplanes. Isolation forest isolation tree construction recursively splits feature spaces by selecting a random feature axis and choosing a random split value between the feature minimum and maximum. Because outliers reside in sparse, low-density regions of feature space, they require far fewer random splits to isolate into leaf nodes compared to normal data points residing in dense clusters. By evaluating the average path length required to isolate a sample across an ensemble of random trees, Isolation Forest assigns an anomaly score. Isolation Forest path length evaluation measures anomaly scores using the average path length equation C, n, equals 2 times the natural log of n-1, plus Euler's constant 0.5772, minus 2 times n-1 divided by n, where n is the sample size. Samples with path lengths significantly shorter than C, n, receive high anomaly scores, identifying them as high-confidence spatial outliers. Local outlier factor, or LOF, evaluates multivariate anomaly scores by comparing local sample densities against neighbor density distributions. For each sample, LOF computes the k-distance and local reachability density relative to its k-nearest neighbors. If a sample's local reachability density is significantly lower than the average density of its neighbors, the sample resides in a sparse region relative to surrounding clusters, earning a high anomaly score. Unlike global distance metrics, LOF detects localized anomalies inside heterogeneous datasets containing clusters with varying spatial densities. Local outlier factor contamination hyperparameters govern decision thresholds for flagging spatial anomalies. Specifying contamination as an expected percentage of outliers instructs the LOF algorithm to set anomaly score thresholds based on sample score quantiles, allowing engineers to tune outlier sensitivity precisely. When evaluating engineering design decisions and architectural trade-offs, developers must balance computational latency against statistical imputation fidelity. Univariate mean or median imputation operates with exceptional speed, requiring simple statistical aggregation during fitting and instantaneous scalar replacement during transformation. For high-throughput real-time serving systems operating within microsecond latency budgets, simple imputer combined with missing indicator provides an optimal balance of execution speed and predictive signal preservation. Conversely, multivariate imputers like KNN imputer or iterative imputer incur massive computational and memory overhead. Computing Euclidean distances across millions of samples in KNN imputer exhibits quadratic time complexity with respect to sample size, transforming real-time feature transformation pipelines into massive computational bottlenecks. Furthermore, during online inference, a KNN imputer must retain the entire historical reference training dataset in memory to locate nearest neighbors for incoming prediction requests, creating severe memory footprint explosion. Engineers must restrict multivariate imputation to offline batch processing workflows where statistical accuracy outweighs execution latency. Another fundamental architectural trade-off involves handling outliers. Explicit row removal versus spatial winsorization and clipping. Naively dropping outlier rows from a training dataset appears simple, but it permanently alters target class proportions and risks purging rare, legitimate edge cases. In high-dimensional spaces, applying multivariate outlier filters too aggressively can silently discard over 30% of a dataset, starving downstream estimators of training data. A far more robust engineering pattern is feature clipping or winsorization. Winsorization truncates extreme distribution tails to fixed percentile thresholds without altering sample size. Implemented using custom transformation functions or percentile bounds, winsorization identifies feature values falling below a lower percentile, such as the first percentile, or above an upper percentile, such as the 99th percentile, and caps them to the boundary values. This capping transformation bounds extreme gradient magnitudes during model training, protecting linear estimators and neural networks from gradient explosion while retaining all sample records in the training set. In a production case study, consider an electronic health record ingestion platform processing patient vitals and laboratory measurements across intensive care units. Incoming patient vectors contain missing lab values due to non-uniform test ordering schedules, alongside extreme physiological spikes caused by sensor disconnects or equipment calibration failures. The clinical machine learning platform must ingest raw patient records, impute missing physiological metrics, strip sensor noise, and calculate real-time patient deterioration risk scores every 60 seconds. Initial pipeline deployments suffered from severe clinical reliability issues. The engineering team initially used listwise deletion, dropping any patient snapshot that contained missing lab metrics. This flawed design purged over 40% of ICU patient records, preventing the risk scoring engine from monitoring high-risk patients who had not received recent blood tests. Additionally, unhandled sensor disconnects injected physiological values of 0 or 9,999 into gradient-boosted decision trees, triggering false mortality alerts and creating alarm fatigue among medical staff. The data engineering team re-architected the clinical data pipeline into a multi-tier imputation and sanitization service. First, they conducted a domain audit to classify missingness regimes across lab parameters, confirming that missing lab tests were missing at random, dependent on patient age and admission category. They implemented a two-stage imputation pipeline using Scikit-Learn, a simple imputer configured with median strategy to handle random missingness, combined with a missing indicator transformer that appended explicit binary flags capturing whether a specific lab had been ordered. Second, for physiological continuous streams such as heart rate and oxygen saturation, they introduced a robust clipping transformer bounded by physiologically plausible medical thresholds, replacing nonsensical sensor disconnect values with missing markers prior to imputation. Third, they wrapped the entire sanitization workflow inside a Scikit-Learn feature union and pipeline structure, validating fit transform parameters against historical patient validation cohorts. The refactored platform restored monitoring coverage to 100% of ICU patients, reduced false mortality alarms by 74%, and maintained real-time patient risk calculations comfortably within 30-second scoring cycles. Troubleshooting and debugging missing value and outlier pipelines requires a systematic audit of mask propagation, numerical precision, and target distribution distortion. A major failure mode in NumPy and Pandas pipelines occurs when missing values silently propagate through linear algebra routines. Standard C-compiled linear algebra libraries do not automatically filter NaN floating point values. If a single NaN value enters a matrix multiplication or principal component decomposition without prior imputation, the matrix product cascades into all NaN entries, rendering the entire output matrix corrupt. Developers must enforce strict assertion checks verifying zero NaN presence prior to passing feature matrices to downstream estimators. Another insidious bug arises from fitting imputation transformers on pre-clipped or corrupted data. If raw sensor data contains placeholder values like -999 to represent missingness, calling simple imputer with default NaN strategies will fail to recognize -999 as a missing value. The imputer treats -999 as a valid numerical magnitude, skewing feature mean calculations and filling legitimate NaN entries with corrupted negative averages. To debug placeholder corruption, engineers must replace custom Sentinel values with standard IEEE NaN floating point representations prior to fitting imputation transformers. Data leakage during outlier filtering presents another subtle debugging challenge. If an engineer computes global IQR bounds or fits an isolation forest across the entire combined dataset before executing cross-validation splits, the outlier bounds incorporate statistical variance from the test set. Outliers in the test set will have influenced training boundaries, skewing validation metrics. To prevent leakage, outlier detectors and clipping boundaries must be fitted strictly inside training folds within automated pipeline wrappers. Finally, developers must audit target variable distributions to ensure outlier removal is never applied indiscriminately to target vectors Y. Applying percentile clipping or isolation forest filtering directly to regression target variables truncates true target ranges, preventing downstream models from predicting extreme target values in production. Outlier sanitization must focus strictly on corrupted feature inputs X, preserving true target variance to ensure models remain capable of forecasting high-magnitude real-world outcomes. Raw data features describe physical phenomena, business events, or system metrics, but they are rarely formatted in a way that maximizes the learning capacity of linear or distance-based algorithms. A linear model, for instance, assumes that the relationship between input features and target outputs is strictly additive and proportional. If the true underlying data-generating process involves nonlinear curves, threshold multiplicative effects, or complex feature interactions, a linear model trained on raw inputs will suffer from high bias and underfitting. Feature engineering is the architectural discipline of applying domain knowledge and mathematical transformations to construct new, highly informative feature representations, enabling simpler models to capture complex nonlinear signals without sacrificing interpretability or computational efficiency. To understand feature engineering mechanics, we must examine mathematical transformation families: polynomial expansion, feature binning, nonlinear monotonic transformations, B-spline representations, cyclical encoding, and weight of evidence encoding. Polynomial expansion, implemented via polynomial features transformers, constructs explicit interaction terms and nonlinear power combinations from existing numerical features. For a two-dimensional feature space containing attributes x1 and x2, a second-degree polynomial expansion generates 6 output features: a constant bias term, the original features x1 and x2, their squared terms x1 squared and x2 squared, and their multiplicative interaction term x1 times x2. Spatializing polynomial feature expansion, imagine a three-dimensional parabolic surface representing a target distribution. A simple two-dimensional linear hyperplane cannot fit this curved surface, resulting in large residual errors. By expanding the two-dimensional input features into a five-dimensional polynomial space, the original curved parabolic surface transforms into a flat hyperplane in the higher dimensional space. A simple linear regression model operating in this expanded five-dimensional space fits the data perfectly, capturing complex nonlinear curvature without requiring complex nonlinear solvers. Feature binning, or discretization, transforms continuous numerical attributes into discrete categorical intervals using K-bins discretizer transformers. Binning operates under 3 primary strategies: uniform binning, quantile binning, and k-means binning. Uniform binning divides the continuous feature range into k-equal width intervals, but it is highly vulnerable to skewed distributions where most bins remain empty while a single bin holds 90% of samples. Quantile binning assigns interval boundaries such that every bin contains an equal number of samples, maximizing entropy and statistical balance. K-means binning uses one-dimensional clustering to discover natural density groupings along the feature axis. Once binned, the continuous feature is one-hot encoded into k-binary indicator columns, allowing linear models to fit distinct stepwise prediction offsets across different numerical ranges. Nonlinear monotonic transformations stabilize variance and normalize skewed, heavy-tailed feature distributions. The logarithmic transformation, y equals log of 1 plus x, compresses wide numerical spans into compact linear ranges, making it ideal for monetary amounts, population counts, or web traffic metrics. Power transformations, such as Box-Cox and Yeo-Johnson implemented via Power Transformer, estimate an optimal power parameter lambda using maximum likelihood estimation to minimize distribution skewness and approximate Gaussian normality. In plain language, homoscedasticity requires that prediction errors remain equally spread across all target ranges, preventing a model from producing tight residuals for small targets while scattering massive errors across large targets. Applying optimal Yeo-Johnson power transforms restores homoscedastic variance across complex continuous feature streams. While Boxcox requires strictly positive feature inputs, Yeo-Johnson extends power transformations to support 0 and negative values. Power transformer Yeo-Johnson optimization maximizes log likelihood functions over transformed Gaussian target representations. During fitting, the transformer evaluates candidate lambda values across a continuous numerical search grid, selecting the power parameter that minimizes skewness and maximizes normal distribution fit. Spline transformations, implemented via spline transformer, represent nonlinear curves using piecewise B-spline basis functions joined at smooth knot positions. B-spline basis function generation relies on the Cox-de Boer recursive formula to evaluate piecewise polynomial curves across knot intervals. To picture this intuitively, the Cox-de Boer formula is a mathematical rule that constructs smooth, flexible curves out of smaller polynomial pieces joined seamlessly at specific boundary points called knots. A B-spline of degree d is defined over a sequence of non-decreasing numerical values called knots. The Cox-de Boer formula constructs basis functions recursively, building degree d polynomials from lower degree step functions. At knot boundaries, B-spline basis functions maintain continuous derivatives up to degree d-1, ensuring smooth mathematical transitions between adjacent intervals while preventing global polynomial oscillations. Spline knot vector boundary conditions define extrapolation behavior beyond observed feature ranges. Clamped knot vectors repeat boundary knot values d+1 times, forcing spline curves to pass explicitly through boundary endpoints. Unclamped knot vectors allow splines to extrapolate smoothly beyond training bounds. Cyclical feature encoding transforms periodic temporal variables into continuous two-dimensional spatial representations using trigonometric sine and cosine functions. Attributes like hour of day, day of week, or month of year exhibit periodic continuity. Hour 23 is temporally adjacent to hour 0. Mapping hour values directly to integers introduces an artificial numerical jump between 23 and 0. By projecting periodic features onto a unit circle using sine of 2π times value divided by period and cosine of 2π times value divided by period, cyclical encoding represents periodic continuity accurately in two-dimensional Euclidean space. Representing a 24-hour daily cycle as sine and cosine components maps hour 23 to coordinates 0.97 and -0.22, and hour 0 to coordinates 0 and 1. In two-dimensional Euclidean space, the distance between hour 23 and hour 0 equals the distance between hour 0 and hour 1. This spatial continuity allows distance-based algorithms and neural networks to process temporal features without boundary discontinuities. Weight of evidence, or WOE, encoding transforms categorical features in binary classification domains based on relative log odds ratios. For each category level, WOE computes the natural logarithm of the proportion of positive target events divided by the proportion of negative target events. In simple terms, weight of evidence measures how strongly a specific category level predicts positive versus negative outcomes, while information value sums those scores into a single metric indicating whether a feature has weak, medium, or strong predictive power. A positive WOE value indicates that the category level increases event probability, while a negative value indicates decreased risk. WOE encoding linearizes categorical relationships relative to log odds, making it a standard feature engineering pattern in credit risk modeling paired with logistic regression estimators. An information value below 0.02 indicates uninformative features. Values between 0.02 and 0.1 indicate weak predictive power. Values between 0.1 and 0.3 signify medium predictive strength. Values between 0.3 and 0.5 indicate strong predictive power. Features with information value exceeding 0.5 should be audited for target leakage before inclusion in production models. When evaluating engineering design decisions and architectural trade-offs, developers must manage the combinatorial explosion of feature dimensionality versus predictive performance. The primary architectural risk of polynomial expansion is exponential dimensionality growth. The number of generated polynomial features scales as O of d to the power of p, where d is the original feature count and p is the polynomial degree. Expanding a modest dataset with 50 original features into a third-degree polynomial space produces over 23,000 output features, instantly causing memory exhaustion, degrading execution speed, and inducing catastrophic overfitting due to multicollinearity. To manage feature explosion trade-offs, engineers must enforce sparse interaction constraints. Rather than invoking blind polynomial expansions across all features, developers should specify interaction-only flags, generating multiplicative cross terms without squared power terms, or selectively target specific subsets of domain-relevant features. Furthermore, pairing polynomial expansions with L1, regularized linear estimators or automated feature selection transformers automatically prunes uninformative interaction terms, preserving model parsimony. Another critical architectural decision revolves around choosing between continuous nonlinear transforms and discretized binning. Discretizing a continuous feature into discrete bins transforms a smooth numerical signal into a step function. While step functions allow linear models to fit arbitrary step offsets, binning permanently destroys intrabin numeric resolution. Two data points falling within the same quantile bin receive identical encoded representations, even if one point lies near the bottom boundary and the other lies near the top boundary. For smooth physical phenomena, nonlinear transforms like Yeo-Johnson or B-splines preserve smooth gradient continuity, whereas for threshold-driven decision domains, such as credit score risk tiers, discretized binning provides superior alignment with domain logic. In a production case study, consider an online real estate valuation platform predicting residential property market values in real time. The raw feature stream includes continuous physical attributes, such as gross living area, lot size, property age, and geographic latitude and longitude coordinates, alongside local neighborhood indicators. The pricing engine must generate accurate property valuations and confidence intervals within 20 milliseconds per API request. The engineering team encountered severe prediction inaccuracies when relying on raw linear models. A baseline linear regression model consistently underpriced high-density luxury urban condos while overpricing large rural agricultural properties. The root cause was twofold. Home values scale non-linearly with square footage, exhibiting diminishing marginal value per additional square foot, while property age interacts multiplicatively with geographic location. A 100-year-old historic home in a prime urban core commands a massive price premium, whereas the same 100-year-old structure in a declining rural area represents a liability. The team re-engineered their feature generation architecture. First, they applied a Yeo-Johnson power transformation to gross living area and lot size, converting skewed square footage distributions into well-conditioned Gaussian features. Second, they implemented localized spatial B-spline transformations on latitude and longitude coordinates. generating smooth two-dimensional geographic basis functions that captured micro-neighborhood pricing variations without manual neighborhood boundary coding. Third, they constructed explicit domain interaction features combining property age with spatial location splines and living area. Fourth, they wrapped these feature generators into an automated Scikit-Learn feature union, feeding the expanded feature space into a regularized ridge regression estimator. The refactored feature engineering pipeline reduced median absolute prediction error by 42%, eliminated geographic systemic bias, and maintained sub-5 millisecond scoring latencies, demonstrating the immense power of domain-driven feature transformations. Troubleshooting and debugging feature engineering pipelines requires auditing multicollinearity, numerical domain boundaries, and out-of-bounds transformation behavior. Multicollinearity occurs when newly engineered features are highly correlated with existing features or other interaction terms. In linear models, severe multicollinearity inflates coefficient variance, causing model weights to fluctuate wildly in response to minor noise in training data. To debug multicollinearity, developers should calculate variance inflation factor metrics across the engineered matrix, dropping features with high VIF scores or applying principal component analysis to decorrelate the feature space. To explain variance inflation factor, or VIF, in simple terms, it is a numerical metric that measures how much the estimation instability of a model coefficient is inflated due to high correlation between independent features. A secondary failure mode involves domain violations during nonlinear mathematical transformations. Applying a standard Box-Cox power transform or natural logarithm to a feature matrix containing 0 or negative values raises severe runtime domain errors or produces negative infinite values. If a real-time data pipeline ingests an incoming transaction payload with a 0 or negative account balance and passes it to an unconstrained log transform, the output fills with negative infinity, crashing downstream estimators. Developers must enforce strict lower bound offsets, such as adding a constant scalar shift before log transforms, or utilize Yeo-Johnson transformers designed specifically to handle negative inputs safely. Out-of-bounds errors during feature binning present another common production bug. When K-bin's discretizer is fitted on training data, it establishes fixed numerical bin edges based on the observed training range. If an incoming production sample contains a value smaller than the minimum training edge or larger than the maximum training edge, default binning transformers may fail to assign the sample to a valid bin or throw out-of-range warnings. Engineers must configure binning transformers with explicit boundary clipping parameters, ensuring that out-of-bounds production values are clipped to the outermost bin boundaries automatically. Finally, managing memory consumption during polynomial expansion requires verifying array sparsity formats. Applying degree 2 polynomial expansion to sparse categorical matrices will convert sparse structures into massive dense arrays if the interaction transformer is not configured with sparse output flags. Engineers must ensure that polynomial features and feature union objects maintain SciPy sparse matrix representations throughout the transformation graph, preventing silent memory blowups and keeping feature engineering pipelines fast, robust, and scalable. In complex machine learning workflows, data preprocessing, feature engineering, and model estimation rarely exist as isolated single-step operations. A production workflow often involves imputing missing numerical attributes, one-hot encoding categorical variables, scaling continuous features, generating interaction terms, and fitting a final predictive model. When these transformations are implemented as ad hoc scripts with manual data handoffs between separate objects, the risk of subtle data leakage, state corruption, and operational failure increases exponentially. Scikit-Learn addresses this architectural challenge through its pipeline abstraction, providing an object-oriented framework for encapsulating end-to-end transformation graphs into unified, immutable, and reproducible objects. To understand pipeline mechanics, we must examine structural composition patterns. The sequential pipeline, the column transformer, the feature union, and the transformed target regressor. The standard pipeline object encapsulates a strictly sequential sequence of transformers followed by an optional final estimator. Spatializing a sequential pipeline, visualize a factory assembly line. Raw data enters the first station, for example, a missing value imputer. The imputer fits its parameters during training, transforms the data, and passes the output matrix directly to the second station, such as a feature scalar. The scalar fits its parameters, transforms the matrix, and passes it to the third station. This sequential data handoff continues automatically until the final station is reached. If the final station is a predictor estimator, invoking fit on the pipeline object triggers fit_transform sequentially down the chain before invoking fit on the final predictor. While a sequential pipeline processes the entire feature matrix uniformly, real-world tabular datasets contain heterogeneous feature types requiring entirely different transformation paths. Numerical columns need imputation and scaling, categorical columns need one-hot encoding, and unstructured text columns need n-gram vectorization. The column transformer solves this heterogeneous routing problem by acting as a spatial data router. Spatializing a column transformer, visualize a multi-track railway switch operator. When a heterogeneous data frame enters the column transformer, the object evaluates column selector rules, splitting the input matrix into distinct column submatrices. Track 1 routes numerical columns to a numerical scaling pipeline. Track 2 routes categorical columns to an encoding pipeline. Track 3 routes text columns to a vectorizer. Each branch transforms its designated columns independently. Once transformation completes, the column transformer horizontally concatenates the output submatrices back into a single unified feature matrix. Column transformer remainder configuration using Boolean mask selectors enables dynamic untransformed column pass-through. Setting remainder to drop purges any input data frame columns that were not explicitly selected by transformer tracks, while setting remainder to pass-through retains unselected columns, appending them untransformed to the right side of the output matrix. Column transformer feature name tracking via get_feature_names_out concatenates transformer track prefixes with original column names, generating descriptive feature labels across complex multi-branch pipelines, allowing downstream explainability tools to trace predictions back to specific preprocessing tracks. Feature union provides parallel feature extraction capabilities. Unlike column transformer, which splits columns across distinct tracks, feature union passes the exact same input matrix into multiple parallel transformer branches simultaneously, horizontally stacking their outputs into an expanded feature space. DAG-like transformation topologies expand pipeline flexibility beyond linear sequential chains. By nesting column transformers inside feature unions and chaining them within sequential pipelines, developers construct complex directed acyclic graph transformation networks. For example, a raw feature table can be split by data type, passed through parallel scaling and encoding tracks, merged into a dense matrix, passed through parallel principal component and spline expansion branches, and finally fed into a regularized estimator, all managed within a single composite object. Transformed target regressor extends pipeline encapsulation to target variables y, applying nonlinear transformations such as logarithmic transforms, to target outputs prior to model fitting, and automatically applying inverse transformations during prediction. When target variables display right-skewed log-normal distributions, such as house prices or medical costs, fitting linear regression models directly on raw target values violates homoscedasticity assumptions. To explain homoscedasticity in simple terms, homoscedasticity is the condition where prediction error variance remains constant across all feature values, preventing a model from being accurate on small inputs while failing wildly on large ones. Transform target regressor applies a logarithmic transform to y before model fitting, and automatically applies an exponential inverse transform to prediction outputs. Crucially, when evaluating predictions, the regressor accounts for log-normal variance adjustments. Transform target regressor residual log-normal variance estimation calculates half the residual mean squared error from log-transform target regressions. Adding half the residual variance to log predictions before exponential backtransformation adjusts for geometric mean bias, ensuring expected value forecasts match true population target means in original physical units. Pipeline objects also implement a sophisticated hyperparameter access protocol using double underscore or dunder parameter routing syntax. In simple terms, dunder syntax acts like a directory path, using two underscores to navigate down into nested transformer objects inside a composite pipeline. When configuring grid search or cross-validation routines over a composite pipeline, individual step parameters are accessed by concatenating the step name, a double underscore, and the target hyperparameter name. For example, referencing a scaling transformer's mean parameter inside a pipeline named preprocessor is written as preprocessor double underscore scalar double underscore with underscore mean. This dunder parameter protocol enables automated search routines to optimize preprocessing hyperparameter choices and final model hyperparameters simultaneously within a single unified validation harness. Custom transformer development requires inheriting from base estimator and transformer mixin, implementing explicit signature contracts. A well-behaved custom transformer defines constructor parameters with default values, stores learned state in trailing underscore attributes during fit, and returns modified arrays from transform. By implementing get underscore feature underscore names underscore out, the custom transformer integrates seamlessly into Scikit-Learn's feature lineage tracking systems. Moving to engineering design decisions and architectural trade-offs, encapsulation versus modular flexibility represents the fundamental trade-off in pipeline engineering. Encapsulating an entire machine learning workflow into a single serialized pipeline object guarantees absolute operational reproducibility. During online serving, an application receives raw payload data, passes it to the pipeline's predict method, and receives target predictions. Preprocessing scaling, missing value imputation, and encoding occur automatically under the hood, completely eliminating manual feature engineering scripts in production handlers and removing entire classes of training serving skew bugs. However, strict pipeline encapsulation introduces trade-offs regarding intermediate state inspection and memory caching. When debugging complex multi-step pipelines, inspecting intermediate feature matrices between hidden steps requires accessing internal named steps attributes or registering custom inspection transformers. Furthermore, during hyperparameter optimization sweeps across heavy pipelines, rerunning expensive initial pre-processing steps, such as text vectorization or missing value imputation, for every single hyperparameter combination incurs massive computational waste. Scikit-Learn mitigates this computational waste by providing built-in memory caching via the memory hyperparameter. By passing a joblib memory directory object to a pipeline, the pipeline automatically serializes and caches the output of each intermediate transformer on disk. When a hyperparameter search reevaluates a pipeline branch with identical upstream parameters, the pipeline skips redundant transformer execution altogether, loading the precomputed feature matrix directly from disk cache. Joblib memory caching rules invalidate disk cache based on function source code hashes and input parameter signatures. When a pipeline wrapped with a Joblib memory object executes, Joblib computes SHA-1 hashes of transformer code strings, hyperparameter values, and input data buffers. If upstream parameters remain unchanged, Joblib loads precomputed transformed matrices directly from disk storage. Joblib memory disk cache maintenance routines prevent storage depletion in automated training pipelines. Configuring cache size limits or clearing expired Joblib cache directories periodically purges obsolete intermediate transformer matrices, reclaiming disk space while maintaining high-speed caching for active pipeline development runs. In a production case study, consider an enterprise e-commerce recommendation platform processing multimodal user activity feeds to predict customer purchase intent. The incoming transaction payloads contain numerical engagement metrics, such as session duration and item click counts, categorical user profile metadata, and unstructured text search queries. The inference engine must process incoming user sessions and predict purchase probabilities within a strict 20 millisecond latency deadline. Initial pipeline attempts relied on fragmented microservices. A Python data processing script cleaned raw JSON payloads and wrote intermediate matrices to temporary database tables. A second script executed feature encoding, and a final scoring container fetched encoded matrices to make predictions. This decoupled design caused frequent production outages. Database write latency spikes caused scoring deadlines to breach, while silent column ordering mismatches between the encoding script and the scoring container led to catastrophic feature misalignment, causing purchase recommendations to collapse. The engineering team unified the entire workflow into a single production-grade Scikit-Learn column transformer pipeline. They defined 3 parallel execution tracks. Track 1 selected numerical engagement metrics, applying a simple imputer paired with a robust scaler. Track 2 selected categorical profile metadata, applying a one-hot encoder with handle_unknown set to ignore. Track 3 selected unstructured search query text, passing string payloads into a TF-IDF text vectorizer transformer. They merged these tracks using a column transformer, appending a gradient-boosted decision tree classifier as the final estimator step. The team validated the composite pipeline using cross-validation, serialized the fitted pipeline as a frozen binary artifact, and deployed it directly into high-throughput inference microservices. In production, the microservice ingests raw session JSON payloads, invoking predict_proba directly on the pipeline object. This unified architecture eliminated database intermediate table writes, completely resolved training-serving feature alignment skew, and reduced end-to-end scoring latency from 45 milliseconds down to 6.2 milliseconds, easily satisfying strict real-time production SLAs. Troubleshooting and debugging pipeline architectures requires a rigorous understanding of column selection scope, signature contracts, and serialization constraints. A common failure mode in column transformer workflows involves column index shifting when input data frames undergo schema updates. If a column transformer selects columns using integer positional indices rather than explicit string column names, inserting a new column into the raw input data frame silently shifts all downstream integer column references. Numerical columns become accidentally routed into one-hot encoders. while categorical strings hit scaling transformers, raising cryptic data type exceptions. To eliminate column shifting bugs deterministically, engineers must select columns using explicit string names or data type selector functions. Another ubiquitous error occurs when integrating custom user-defined transformations into a pipeline via function transformer. Function transformer converts arbitrary Python functions into Scikit-Learn compatible transformers. However, if the underlying custom function is defined using inline lambda expressions or unpicklable nested closures, serializing the pipeline using standard object serialization protocols will fail with pickling exceptions during artifact export. Developers must define custom transformation logic inside top-level named functions or inherit directly from Scikit-Learn's base estimator and transformer mixin classes, implementing explicit fit and transform methods to guarantee clean serialization. Signature contract violations represent another frequent debugging challenge when authoring custom transformers. Scikit-Learn estimator contracts mandate that the fit method must always return self, and that both fit and transform methods must accept positional matrix arguments X and optional target arguments Y. If a custom transformer's fit method omits returning self, attempting to chain the transformer inside a sequential pipeline will raise an attribute error stating that NumType has no attribute transform. Finally, managing sparse matrix output propagation within column transformer workflows requires careful inspection of dense threshold parameters. If a column transformer merges a sparse text vectorizer track with a dense numerical scaling track, the transformer evaluates the overall matrix sparsity ratio. If sparse outputs fall below predefined sparse thresholds, column transformer automatically coerces the entire merged output into a dense matrix, potentially triggering massive RAM allocation spikes. Engineers must tune sparse threshold parameters explicitly or enforce sparse representations throughout pipeline subtracks, keeping memory footprints minimal and execution speed fast. A machine learning system that produces high predictive performance on a single developer workstation but cannot be reproduced deterministically across team environments or cloud infrastructure is an engineering liability. In numerical computing, subtle non-deterministic behaviors, unseeded pseudorandom number generators, platform-specific floating point variations, and unmonitored memory leaks ruin production deployments. Debugging machine learning software requires moving beyond standard syntax validation to audit low-level execution state, memory allocations, CPU profiling graphs, and random state propagation. To understand reproducibility mechanics, we must examine foundation pillars: pseudorandom number generator state seeding, environment variable hash seeding, hardware-accelerated deterministic execution flags, floating point precision standards, and memory execution profiling interfaces. Pseudorandom number generators produce sequences of numbers that simulate statistical randomness while remaining completely deterministic functions of an initial seed integer. When you instantiate an estimator or random splitting utility in Python, passing an explicit random state integer initializes the underlying generator state vector, such as the Mersenne twistor state array. Given the exact same seed integer, the generator emits the exact same sequence of pseudorandom numbers across every run. However, setting a random state parameter within a high-level Scikit-Learn function is insufficient to guarantee end-to-end reproducibility, because Python and underlying C libraries maintain independent random number generators. At the operating system level, Python initializes a dynamic string hashing seed controlled by the pythonhashseed environment variable. If pythonhashseed is not set to a fixed integer prior to process launch, Python generates a random hash seed upon interpreter startup, This random hash seed alters dictionary key iteration orders and set traversal sequences between different process runs. If a data preprocessing script iterates over a set of feature names to construct a matrix, unseeded hash randomness alters column ordering between runs, corrupting model training. Furthermore, compiled linear algebra libraries such as OpenBLAS, Intel MKL, and CUDA runtimes introduce low-level nondeterminism through parallel thread scheduling. In multi-threaded matrix operations or atomic GPU floating-point reductions, parallel worker threads add floating-point numbers in non-deterministic orders. Because floating-point addition is non-associative due to finite precision rounding, changing the order of parallel floating-point additions alters the final least significant bits of matrix products. Achieving bit-for-bit numerical reproducibility demands setting deterministic execution flags across host environment variables, configuring OpenMP thread counts, and forcing GPU runtimes to use deterministic algorithms. Hardware-accelerated deterministic execution on CUDA runtimes requires configuring environment variables and runtime flags explicitly. On GPU devices, parallel reduction algorithms use atomic floating-point addition instructions that execute in non-deterministic orders depending on thread warp scheduling. To force deterministic GPU execution, developers must set the cublas_workspace_config environment variable to 4096:8 or 16:8. In plain English, setting this workspace configuration reserves a fixed memory area on the GPU, preventing parallel matrix multiplication threads from adding numbers in random orders and guaranteeing bit-for-bit prediction parity. Floating-point precision degradation presents subtle numerical stability challenges in machine learning pipelines. IEEE 754 floating-point standards specify binary representations for floating-point numbers. A 32-bit single precision float uses 1 sign bit, 8 exponent bits, and 23 mantissa precision bits, providing approximately 7 decimal digits of precision. A 64-bit double precision float uses 11 exponent bits and 52 mantissa bits, providing 15 decimal digits of precision. IEEE 754 double precision floating point formats provide 52 mantissa bits, representing approximately 15 decimal digits of precision. Single precision formats provide 23 mantissa bits, representing 7 decimal digits. Accumulating loss gradients across millions of training steps in single precision risks catastrophic mantissa underflow, where small feature gradients underflow to 0 during backpropagation. Floating point subnormal number handling controls hardware execution latency during gradient underflow. When floating point values drop near 0, CPUs enter subnormal representation modes, incurring heavy performance penalties on arithmetic instructions. Enabling flush to 0 hardware flags forces subnormal floats to 0 instantly, preserving SIMD execution speed in deep optimization loops. Mixed precision gradient scaling prevents underflow in half-precision floating-point training loops. Gradient scaling transformers multiply loss values by a dynamic scale factor before backward passes, inflating gradient magnitudes to fit within 16-bit floating-point ranges, and unscaling gradients before optimizer steps. Utilizing double precision accumulation or loss scaling guarantees numerical gradient stability in deep optimization loops. Execution profiling mechanics allow engineers to audit CPU cycle allocation and memory heap growth. CPU profiling, implemented via cProfile or flame graph visualizers, intercepts function calls during execution, recording call frequencies, total execution time, and cumulative time spent inside nested functions. Spatializing a CPU call graph. Imagine a hierarchical execution tree where wide nodes represent functions consuming massive CPU time. Memory profiling, operating via memory tracking hooks or heap snapshot analyzers, monitors process memory allocation over time, tracking memory allocations down to specific line numbers and identifying memory leaks where allocated objects fail to be garbage collected. Python garbage collection inspection routines identify circular object references that evade standard reference counting. When data processing pipelines instantiate custom objects with circular references, Python's generational garbage collector periodically scans heap memory to break reference cycles. Monitoring garbage collection logs via the GC module isolates uncollected circular references, ensuring memory buffers are freed promptly. Memory allocation profiling using native Python tracking hooks isolates memory leaks down to specific source lines. The built-in Tracemalloc module intercepts Python heap allocations, recording allocation tracebacks and memory block sizes. By capturing memory snapshots before and after executing data processing loops, developers compute memory deltas, identifying uncollected PY-object allocations, persistent caching lists, or unreleased C-extension buffer references that cause memory footprint bloat. Evaluating engineering design decisions and trade-offs in reproducible systems requires balancing absolute determinism against computational performance. Forcing absolute bit-for-bit determinism on hardware-accelerated GPU runtimes requires disabling asynchronous parallel reduction kernels and forcing atomic operations to run sequentially. Disabling parallel optimizations can incur a 10 to 30% throughput penalty on high-performance training runs. For research exploration and hyperparameter sweeps, minor floating-point variations in least significant bits are often acceptable trade-offs for faster execution. But for regulatory auditing, financial compliance, and clinical applications, the engineering trade-off strongly favors absolute determinism. Another critical architectural decision revolves around global random seeding versus explicit object-level random state propagation. Setting global random seeds at the top of a script using global seed functions appears convenient, but it creates hidden state dependencies across execution modules. If a third-party library call internally consumes a random number from the global generator, inserting or removing a single logging call shifts the global generator state, causing all downstream estimators to receive different random sequences. Best practice demands explicit object-level random state propagation, passing explicit random state parameters to every individual estimator, cross-validation splitter, and feature generator object. Unit testing machine learning code introduces another trade-off: testing speed versus integration coverage. Standard software unit tests execute in milliseconds, validating deterministic logic. Machine learning integration tests, which involve fitting estimators on real datasets, can run for minutes or hours. To maintain fast, continuous integration pipelines, engineers utilize synthetic dataset fixtures generated via deterministic data generators. Synthetic fixtures generate small, highly structured numerical matrices in memory, allowing unit tests to verify pipeline fitting, schema transformations, and prediction output shapes within microsecond execution budgets. In a production case study, consider a quantitative algorithmic trading firm deploying real-time market regime classification models across global co-located trading servers. The trading strategy requires that feature scaling transformers, volatility models, and trade signal classifiers produce bit-for-bit identical outputs when replaying historical market tick data across Linux, Mac OS, and Windows developer environments. The engineering team discovered severe model drift during production audits. Back-tested trading strategies executed on developer workstations produced different trading signals than the live execution containers deployed in cloud data centers, despite consuming identical tick data. The divergence was traced to three root causes: unseeded Pythonhashsed environment variables altering feature dictionary order, multi-threaded open-BLAS matrix multiplication changing floating point rounding order, and unclosed memory references in a custom feature transformer causing heap allocation drift. The quantitative platform team implemented a comprehensive reproducibility architecture. First, they established an immutable container environment spec where Pythonhashsed, CUDA deterministic flags, and single-threaded BLAS execution variables were explicitly pinned. Second, they replaced global random seeding with explicit object-level random state parameters propagated through a master configuration dictionary. Third, they introduced automated regression testing inside their continuous integration pipeline. Every pull request triggers a bit-for-bit verification test that fits the model against synthetic market fixtures, computing SHA-256 cryptographic hashes of output prediction matrices. If a code change alters prediction output hashes by a single bit, the build pipeline fails automatically. This deterministic architecture restored complete parity between backtest simulations and live market execution. Troubleshooting and debugging numerical software failures requires a structured diagnostic protocol. Memory leaks are among the most difficult bugs to isolate in data science applications. A memory leak in Python typically occurs when objects retain ungarbage-collected references inside global lists, object caches, or C extension wrappers. For example, accumulating intermediate data frames inside a global list during a long training loop prevents Python's reference-counting garbage collector from releasing underlying memory blocks. Developers can debug memory leaks using memory tracking utilities like Tracemalloc, taking heap snapshots before and after execution loops to identify growing object types. Silent precision degradation represents another dangerous failure mode. Modern GPU accelerators often default to 16-bit half-precision or float 16 floating-point formats to maximize matrix multiplication throughput. However, accumulating gradients or computing variances in half-precision can trigger underflow or overflow, filling matrices with NaN values or rounding subtle feature gradients to zero. Engineers must audit numerical precision across performance-critical transformations, utilizing mixed precision patterns where sensitive statistical aggregations, such as variance and mean computations, are executed in 32-bit or 64-bit precision, while heavy matrix multiplications run in fast lower precision. Diagnosing training serving skew requires auditing data pipeline transformations at the individual feature level. Training serving skew occurs when feature values calculated during online inference differ statistically from values calculated during offline training for the exact same underlying event. To isolate training serving skew, developers should implement feature logging sidecars in production microservices, capturing raw input payloads and output feature vectors. Comparing serialized production feature vectors against offline backtest vectors using matrix delta assertions immediately isolates which specific transformer step introduced transformation drift. Finally, managing C extension segmentation faults requires understanding native binary crash boundaries. GDB native debugger stack trace analysis isolates C extension segmentation faults down to specific C/C++ source code lines. When a compiled C extension crashes the Python process with a native memory fault, running Python inside GDB intercepts the crash signal. Issuing backtrace commands inside GDB displays the full CCall stack, identifying memory allocation bugs, null pointer dereferences, or buffer overflows inside custom C extensions. Isolating native crashes ensures that custom numerical extensions remain stable, safe, and production-ready. As machine learning projects grow from disposable exploratory scripts into enterprise software systems, managing workspace structure and code organization becomes paramount. A common failure mode in data science teams is the accumulation of monolithic, unorganized Jupyter notebooks filled with out-of-order execution states, hard-coded file paths, and duplicated pre-processing logic. While interactive notebooks are invaluable for rapid data exploration and visual diagnostics, relying on notebooks as production code units creates severe technical debt. Building scalable, maintainable machine learning systems requires establishing a clear boundary between interactive scratchpads and modular, production-grade Python package architectures. Modular machine learning repository architectures structure production logic within testable source packages while reserving notebooks for exploratory research. Combining PyProject.toml packaging manifests with DVC data versioning pointers establishes an immutable, enterprise-grade machine learning software engineering workflow. To understand notebook execution mechanics and project layout spatialization, we must analyze the internal structure of interactive notebooks versus production package trees. A Jupyter Notebook file is not a pure Python source file. It is a JSON document containing a structured array of code cells, markdown cells, execution count metadata, and embedded output payloads. When you execute a cell in a notebook, the code string is sent to the background kernel process, which evaluates the code and updates its global state dictionary in memory. The Jupyter 0MQ messaging protocol orchestrates client-kernel communication across 5 specialized socket channels: shell, IOPub, STIN, control, and heartbeat. To visualize this architecture, picture 0MQ sockets as 5 high-speed background communication pipes that pass messages back and forth between your web browser interface and the background Python execution process. The shell channel handles code execution requests and returns execution replies. The IOPub channel broadcasts execution results, stout text, stare tracebacks, and display graphics asynchronously to all connected frontends. The STIN channel handles interactive user inputs. The control channel handles high-priority kernel interrupts and shutdown requests. The heartbeat channel sends periodic ping-pong pulses between frontend and kernel to monitor process health. Jupyter 0MQ message schemas serialize execution requests into structured JSON objects containing header metadata, parent header references, metadata flags, and content payloads. When a user executes a cell, the shell channel transmits an execute_request message containing the raw code string, while the kernel processes the request, emitting status messages and stream output payloads over the IOPub channel. Jupyter 0MQ STIN sockets enable interactive user input prompting during notebook cell execution. When a kernel encounters an input prompt statement, it transmits an input_request message over the STIN channel, pausing cell execution until the user submits a response string from the notebook interface, maintaining responsive interface control during interactive debugging sessions. Spatializing notebook execution state, imagine a global memory pool that persists across cell runs. Unlike a traditional Python script, which executes linearly from top to bottom in a fresh, isolated interpreter process every time it is invoked, a notebook allows cells to be executed in arbitrary, nonlinear orders. If an engineer executes cell 10, which mutates a global data frame, and then scrolls back up to re-execute cell 3 operates on the mutated state produced by cell 10. The execution order is recorded only by the incremental cell execution prompt counters, such as in bracket 25. If the notebook is closed and re-executed from top to bottom, the nonlinear execution sequence vanishes, causing script failure or producing different numerical results. Production project architecture solves this state fragility by organizing code into a modular directory hierarchy. Spatializing a standard machine learning package tree, picture a clean, compartmentalized directory structure. At the root of the project sits the configuration manifest, such as piproject.toml configuration manifests defined under PEP 517 and PEP 518 standards alongside environment lock files. A piproject.toml file replaces legacy setup.py build scripts, declaring build system requirements, such as setup tools, hatch or flit, and defining project metadata, dependency bounds, entry point scripts, and tool configuration settings in a single standardized file. Automated project packaging manifests configured via piproject.toml define build backends, dependency constraints, and CLI entry points in a single standardized file, ensuring reproducible package builds across modern environment installers. Core production code resides within a dedicated source directory, typically structured using the src layout under a top-level package folder. Inside the source directory, functionality is decoupled into single responsibility modules. A data ingestion module handling file I/O and remote database connections, a preprocessing module containing custom Scikit-Learn transformers, a model architecture module defining estimator configurations, and a pipeline module orchestrating end-to-end workflows. Outside the source directory sit distinct top-level folders. A data directory divided into raw, interim, and process data tiers. A models directory storing serialized, version pipeline artifacts. A tests directory containing automated unit and integration tests. And a notebooks directory reserved strictly for exploratory research scratchpads. Dataset versioning architectures using dataset version control, or DVC, store cryptographic MD5 hashes of raw data files inside lightweight text tracking files committed to Git. When a developer executes DVC pull commands, DVC reads the hash pointers from Git tracking files, fetching corresponding binary data files from remote cloud storage buckets like S3 or GCS. This decoupled data versioning pattern keeps Git repositories lightweight while ensuring that every code commit is permanently linked to its exact historical dataset version. DVC pipeline stage definitions in dvc.yaml structure reproducible data processing DAGs. A dvc.yaml manifest specifies command line execution steps, input file dependencies, and output dataset targets, re-executing only affected downstream processing stages when upstream files change. Moving to engineering design decisions and architectural trade-offs, developers must decide when to keep code inside interactive notebooks and when to refactor logic into modular Python packages. Interactive notebooks excel during the initial exploratory data analysis phase. The ability to execute small code blocks incrementally, inspect intermediate data frames, render diagnostic plots, and document hypotheses using rich markdown makes notebooks unmatched for research exploration. However, using notebooks for production pipelines introduces severe trade-offs. Code duplicated across multiple notebooks cannot be unit tested automatically using standard testing frameworks. Version control tools like Git treat JSON notebook files as massive text blobs. Merging concurrent Git branches containing notebook execution outputs leads to catastrophic merge conflicts in JSON metadata arrays. Furthermore, importing functions directly from one notebook into another requires complex, fragile hack libraries that bypass standard Python import mechanisms. Modern engineering best practice enforces a strict refactoring workflow. Notebooks are used strictly as disposable execution clients that import clean, tested logic from the core source package. As soon as a data cleaning routine, feature engineering function, or visualization block stabilizes in a notebook scratchpad, the developer refactors the code out of the notebook cell and packages it into a named function or class inside the src package directory. The notebook then imports the function from the package, passing data through clean function signatures. This modular approach preserves the interactive benefits of notebooks for visualization while ensuring that core business logic remains fully testable, version controllable, and deployable in production. Another key architectural decision involves project packaging layout, src layout versus flat layout. In a flat layout, the package directory sits directly in the project root alongside configuration files and tests. Flat layouts are simple, but they introduce silent import traps. Running tests or scripts from the root directory can cause Python to import modules directly from the local root folder rather than from the installed package environment, masking missing package build configurations. The src layout prevents this import ambiguity by placing package modules inside a src subfolder. To import from a src layout during development, the package is installed in editable mode using pip install e, ensuring that import resolution mirrors production installation mechanics deterministically. In a production case study, consider a healthcare analytics firm modernizing a legacy patient risk prediction engine. The original codebase consisted of a single 40,000-line monolithic Jupyter notebook maintained by multiple data scientists. The notebook contained hard-coded local file paths, out-of-order cell execution dependencies, raw SQL query strings, manual missing value imputations, and inline model fitting logic. This monolithic setup created immense operational friction. Training the model required a data scientist to open the notebook manually, run cells sequentially while monitoring for memory crashes, and copy-paste prediction outputs into CSV files for deployment. Upstream database schema changes broke notebook cells silently, while attempting to merge Git branches across 3 data scientists resulted in unresolvable JSON merge conflicts, halting development for weeks. The platform engineering team executed a systematic architectural refactoring. First, they established a standardized repository layout using the src layout, initializing environment locking and automated test runners. Second, they extracted raw SQL queries into a dedicated database module within the src directory, implementing parameter validation and schema checks. Third, they refactored manual data cleaning and feature engineering cells into custom, reusable Scikit-Learn transformers stored within a preprocessing module. Fourth, they unified training and inference execution into CLI command line scripts exposed via entry points. Fifth, they established an automated CI/CD pipeline that runs fast static linters like rough to enforce formatting, static type checkers like mypy to verify type signatures, and test runners like Pandas to execute unit and integration test suites against synthetic data fixtures on every Git push. Dataset version control synchronization using DVC remote storage handlers manages data pipeline facts across team environments. Running DVC push uploads hash data files to remote object storage, while DVC pull retrieves matching data versions onto developer workstations. The legacy monolithic notebook was replaced by a clean, 5-line demonstration notebook that imported the installed SRC package, invoked the pipeline, and rendered diagnostic ROC curves. This modular project architecture eliminated Git merge conflicts, automated model retraining in cloud pipelines, and reduced end-to-end deployment time from days of manual notebook execution down to automated 5-minute CI/CD releases. Troubleshooting and debugging project structure and notebook workflows requires a clear understanding of package import paths, kernel state management, and version control hooks. One of the most prevalent bugs in notebook development is the module not found error when attempting to import local SRC modules into a notebook cell. This occurs because the Jupyter kernel initializes its system path based on the directory containing the notebook file. If the notebook resides inside a nested notebook subfolder, Python cannot locate the SRC directory located at the project root. To debug package import failures, engineers must avoid manual system path append hacks inside notebook cells. Instead, install the local project package in editable mode within the active virtual environment using package installation tools with the editable flag. Installing in editable mode creates a package link inside the environment's site packages directory pointing back to the project root. Consequently, the Jupyter kernel resolves imports to the local SRC package natively, regardless of which subdirectory the notebook is launched from. Another frequent failure mode involves phantom variable imports and state corruption caused by hidden out-of-order cell executions. If a developer deletes a variable definition cell in a notebook but does not restart the kernel process, the variable remains alive in the kernel's memory dictionary. The notebook continues to execute successfully in the developer's session, but fails instantly when run in a fresh environment. To detect and eliminate phantom variable state, developers must enforce a strict validation rule. Before committing any notebook to version control, restart the Jupyter kernel and execute all cells sequentially from top to bottom, verifying that execution counters proceed linearly from 1 to n without errors. Jupyter's 0MQ control channel sockets handle high-priority kernel signals, such as execution interrupts and soft restarts. When a user clicks interrupt kernel, the frontend transmits an interrupt message over the control channel, instructing the kernel process to raise a keyboard interrupt exception inside the running thread, decoupling control signals from standard shell channels so long-running cells can be interrupted instantly. Finally, managing version control bloat caused by raw notebook files requires configuring automated Git pre-commit hooks. Committing unstripped notebooks fills Git repositories with megabytes of base 64, encoded image strings and execution counts, causing repository bloat and merge collisions. Configuring pre-commit hooks using notebook stripping tools automatically clears cell outputs and metadata counters prior to Git commits. The clean, output-stripped JSON file is committed to version control, keeping repositories lean, merge-friendly, and maintainable. Continuous integration testing and reproducible deployment practices form the bedrock of robust machine learning software engineering. By systematically decoupling execution environments, optimizing contiguous memory buffers in NumPy, leveraging columnar copy-on-write transformations in Pandas, encapsulating transformation pipelines in Scikit-Learn, and enforcing strict lock file immutability across modular project structures, you guarantee that your data processing pipelines remain deterministic, scalable, and resilient against real-world production drift across all deployment environments. Building enterprise machine learning software requires continuous vigilance across all layers of the engineering stack. By combining deep theoretical understanding of memory pointers, C-extension ABI compatibility, vectorization strides, columnar Apache Arrow backends, Scikit-Learn estimator contracts, and deterministic execution flags, software engineers transition from ad hoc data science scripting to constructing robust, scalable, and production-grade artificial intelligence systems. Congratulations on completing this masterclass on Python and essential tools for machine learning engineering. Throughout this comprehensive lesson, we have built a rigorous mental model of the foundational software stack that powers modern artificial intelligence. We explored low-level environment isolation across virtual environments and Conda binaries, unpacked the memory strides and C-contiguous buffer mechanics of NumPy arrays, mastered column-oriented data wrangling and copy-on-write semantics in Pandas, demystified Matplotlib's object-oriented rendering hierarchy, mastered Scikit-Learn's estimator API contracts and pipeline encapsulation, constructed robust feature engineering and imputation workflows, and established deterministic, reproducible project architectures. By mastering these core engineering primitives, you possess the structural mindset required to design, debug, and deploy state-of-the-art machine learning systems with absolute confidence.